Buongiorno a tutti e benvenuti alla prima edizione del convegno New Times, che è l'acronimo che ci siamo dati per New Trends in Material Science and Engineering, una conferenza virtuale che si terrà dal 14, cioè da oggi, fino al 18 di questa settimana. Sono Carlo Cantalini, il chair della conferenza del Dipartimento di Ingegneria Industriale e dell'Informazione e di Economia dell'Università dell'Aquila e vi introdurrò molto brevemente sul nostro convegno. Sostanzialmente l'obiettivo della nostra conferenza è quella di creare un forum sulle nuove tendenze della scienza e tecnologia dei materiali. In sostanza ci aspettiamo di mettere insieme ingegneri dei materiali, chimici e fisici che hanno al centro delle loro ricerche la sintesi ma anche la produzione industriale di materiali, fintanto le loro applicazioni. Ed è proprio in relazione alle applicazioni che abbiamo tentato di schematizzare questo convegno in 6 aree tematiche che spaziano sostanzialmente la prima giornata nel campo della sensoristica ambientale, per poi svilupparsi nei materiali per lo sviluppo sostenibili, quindi materiali per energia, materiali per il trattamento acque, per poi andare avanti le successive giornate sulle materiali per nanobiotecnologie, nanostrutture e coatings. Lo stesso ministro della transizione ecologica, il collega Roberto Cingolani, ha voluto partecipare con un messaggio registrato per darci gli auguri per questa nuova conferenza e per sottolineare l'attualità del tema che noi andiamo a proporre oggi. Molto brevemente, il congresso ha avuto un discreto successo con 170 partecipanti. Il congresso ha il patrocinio dell'INSTM e poi lasceremo la parola al presidente, la professoressa Bondioli, che ci darà qualche informazione. Inoltre vi annuncio una cosa a me molto grata, che è quella di aver istituito il premio Giovanni Schippa per i giovani ricercatori di età inferiore a 35 anni che si saranno distinti in questo congresso per quanto riguarda non solo il loro curriculum ma anche per la loro presentazione. Questo premio AIMA, questo premio per Giovanni Schippa sarà conferito in occasione del convegno della nostra associazione AIMAT che si terrà a Cagliari. Quindi a questo punto io lascerei la parola al nostro magnifico rettore, il professore Edoardo Alesse, per i suoi saluti. Grazie Edoardo.
Grazie a te Carlo per avermi invitato a portare i saluti dell'Ateneo in questo convegno così importante, perché rappresenta una delle culture notevoli della nostra università, un pezzo di storia, come tu hai fatto capire parlando del professor Schippa. L'Università dell'Aquila è un pochino nata intorno a queste figure e a questa cultura. Io ti sono molto grato per ricordarcelo in questi 3-4 giorni in cui parlerete di scienza dei materiali. Ti ringrazio per l'attenzione, sono felice che l'Università dell'Aquila possa ospitare questo evento. Ho avuto modo di leggere un pochino il programma e è davvero interessante. Voglio dire che i nuovi materiali per tante finalità come la sensoristica, il trattamento dell'acqua, la conversione dell'energia e le nanobiotecnologie sono argomenti centrali della scienza moderna, ai quali io non sono un esperto del settore, ma a questi temi sono abbastanza legato anche come medico e come biotecnologo, perché sono cose che ci interessano e ci sono molto molto vicine. Quindi, pur non definendomi un esperto della scienza dei materiali, apprezzo molto l'attenzione che avete posto in questo programma, così come apprezzo il fatto di aver voluto istituire 2 premi che poi attribuirete in un momento successivo nella memoria di Giacomo. Io credo che le istituzioni debbano identificarsi con la loro storia e debbano avere sempre a mente il ricordo di chi ci ha preceduto in maniera importante, in maniera qualificata, le nostre pietre miliari, tanto per intenderci. Io oggi non potrò stare a lungo con voi perché ho altre cose da fare, però cercherò di connettermi di nuovo durante questo congresso, perché ad alcune tematiche, ad alcuni interventi sono davvero interessato e mi farà piacere sentirvi come ricercatore. Un'ultima cosa voglio dire, tra le tematiche rilevanti vi è un concetto centrale alla società moderna, che è quello di sostenibilità ambientale. Ecco, io voglio dire che apprezzo molto anche questo richiamo, perché questo è uno dei temi davvero rilevanti su cui dovremmo agire in maniera proattiva come Ateneo, e che è parte centrale anche del piano strategico del Rettore, che lo ha voluto individuare come uno degli importanti temi di sviluppo dell'Ateneo. Ecco, detto questo, non vi rubo altro tempo, perché ritengo che la parte scientifica abbia il diritto di avere tutto il tempo necessario per potersi espletare. Le mie sono più altro che chiacchiere, ma sono chiacchiere che vengono dal cuore verso un gruppo di persone delle quali ho la massima stima e che ringrazio nuovamente per quello che stanno facendo. Buona giornata.
Grazie Rettore, molto gentile, grazie della tua disponibilità. Poi adesso proseguiamo anche con piccole introduzioni e piccoli saluti. Se è in linea il nostro direttore del nostro dipartimento, Walter D'Ambrogio, non lo vedo sulla mia griglia in questo momento. E allora darei subito la parola alla professoressa Bondioli per dirci un po' qualcosa su la vostra partecipazione. Grazie.
Magnifico Rettore, care colleghe e cari colleghi, caro Carlo, porgo innanzitutto il saluto del Consorzio Italiano per la Scienza e Tecnologia dei Materiali, che ho l'onore di rappresentare, e il mio personale a tutti i colleghi che vedo connessi per seguire questa cerimonia di inaugurazione e la prima giornata dei lavori. È davvero con grande gioia che INSTM ha partecipato da subito e ha voluto appoggiare da subito il comitato organizzatore di questa conferenza, non solo con il patrocinio, ma anche proprio per riconoscere l'importanza che questo convegno ha per lo scambio e la crescita di nuovi ricercatori, facendosi promotrice di 2 premi per giovani ricercatori Under 35, i cui vincitori verranno annunciati nell'ultima giornata di lavori in base alla loro produzione scientifica e la qualità del lavoro che presenteranno al convegno. Come sapete, obiettivo del consorzio INSTM, a cui ad oggi afferiscono 50 università italiane, sostanzialmente tutte quelle in cui viene condotta attività di ricerca nell'ambito dei materiali avanzati e delle relative tecnologie, e infatti promuovere l'attività di ricerca che viene svolta nelle attività consorziate, fornendo al contempo supporto organizzativo, tecnico e finanziario. Il numero di afferenti ad oggi è di circa 2700 tra professori di ruolo, ricercatori universitari, titolari di assegno di ricerca, borse di studio, è in costante aumento, e quindi INSTM ha un po' il ruolo di coordinare in modo efficiente una massa critica di competenze che sono in grado di affrontare al più alto livello di competitività progetti di ricerca innovativi in ambito regionale, nazionale e europeo, ma anche di supportare iniziative rivolte allo sviluppo del trasferimento tecnologico, offrendo efficaci opportunità di interazione tra il mondo accademico e la realtà industriale. Pochi minuti per raccontare alla nostra comunità quello che viene stato fatto nel 2020 e che magari non ha avuto, a causa appunto delle particolari situazioni nella quale ci siamo trovati, particolare risalto. Abbiamo costituito un centro GISE, il Centro di Riferimento Nazionale per il Sistema di Accumulo Elettrochimico di Energia, che è un soggetto non solo in grado di proporsi come unico interlocutore nei confronti del tessuto industriale nazionale e internazionale, ma anche di configurarsi come un partner nelle operazioni sinergiche pubblico-privato che costituiranno il futuro europeo nel settore dell'accumulo dell'energia. Il centro è di fatto il più grosso polo nazionale nel campo della ricerca e sviluppo di materiali avanzati per le tecnologie di accumulo energetico, in quanto ad esso afferiscono 14 gruppi di ricerca di università e di politecnici, più di 70 ricercatori di levatura internazionale con un patrimonio strumentale di estremo valore. Altro tema importante è l'idrogeno e la sua filiera, su cui NSTM ha centrato il suo progetto strategico presentato al MUR per l'FFO del 2020, che ha come obiettivo principale usare la complessa e vasta attività di NSTM per creare un centro virtuale sulla filiera dell'idrogeno, al fine di realizzare molteplici obiettivi, tra cui sicuramente agire da interfaccia compressiva e multidisciplinare verso il mondo produttivo è sicuramente uno degli obiettivi principali in una fase dove nei piani relativi al Green Deal e al Recovery Plan è sottolineata la necessità di intensificare l'interazione tra accademia e industria. Concludo questo breve saluto invitando tutti i presenti al prossimo convegno INSTM che si terrà a gennaio 2022, ma soprattutto ringraziando gli organizzatori per il loro forte impegno per voler creare, dopo tanti mesi in cui alla nostra comunità non è stato possibile ritrovarsi, questo importante momento di condivisione e scambio di tutte quelle attività di ricerca che di fatto, lo sappiamo bene, nei nostri laboratori non si sono mai fermate. Quindi davvero grazie Carlo per aver creato questo momento di condivisione. Buon lavoro a tutti.
Grazie Federica, grazie, ti ringrazio molto. Effettivamente c'era un motivo di ripartenza molto importante da parte nostra e quindi è un buon viatico questo qui. Vedo che si è anche collegato il nostro direttore del Dipartimento di Ingegneria Industriale, il professor D'Ambrogio, al quale lascio la linea per un breve saluto. Prego Walter.
Sì, grazie Carlo, grazie professor Cantalini. Allora io colgo questa occasione per anzitutto complimentarmi con il gruppo del professor Cantalini che anche in questa difficile occasione è riuscito a organizzare un evento congressuale seppur a distanza, ma che comunque sta portando avanti e consente di di presentare l'attività scientifica che, come si diceva, ha continuato ad andare avanti in tutti questi mesi, nonostante le limitazioni che abbiamo avuto per l'accesso ai laboratori, per le frequentazioni, per il numero di persone, eccetera. E quindi questo è importante perché è importante che l'attività scientifica, ma anche quella di presentazione dei risultati, di discussione dei risultati e quindi di pubblicazione non si interrompa. E poi mi fa molto piacere questa larga partecipazione appunto sia a livello nazionale che internazionale per questo evento che spero riesca bene e riesca a tenere nella giusta considerazione sia il nome il prestigio dell'Ateneo aquilano che quello del nostro dipartimento, che è un dipartimento che ha molte anime, ma una di queste molto importante è quella che riguarda l'ingegneria chimica. Quindi io non mi dilungo oltre nei saluti perché è sempre bene lasciare spazio ai lavori. Quando mi trovo a congressi dalla vostra parte, ovviamente i saluti iniziali fanno sempre piacere, ma insomma è bene che siano brevi e quindi a questo punto vi lascio ai vostri lavori che spero procedano bene con soddisfazione di tutti. Grazie e buon lavoro.
Grazie Walter, molto perspicace il tuo intervento. Allora do una notazione tecnica, a questo punto mandiamo il messaggio preregistrato del ministro Cingolani, dopodiché si va direttamente nell'aula dove inizia il convegno, per cui colgo l'occasione per ringraziare di nuovo tutti coloro che ci hanno dato il loro viatico e il loro saluto e ci ritroveremo sull'aula della prima sessione del convegno. Quindi potete trasferirvi anche, rimanete sempre su questo link, dopodiché si aprirà la finestra del convegno. Grazie a tutti, adesso mandiamo il contributo del Ministro. A di nuovo, presto, arrivederci.
Cari ex colleghi, salve a tutti, mi fa piacere salutarvi per questa First International Virtual Conference su Material Science and Engineering. Non mi aspettavo in questo punto della mia esistenza di cambiare così repentinamente mestiere, sia pure per un periodo molto breve, però devo dirvi che pur trattandosi di una attività da ministro, comunque continuo ad avere a che fare con tutte le cose che ho fatto e studiato, peraltro con molti di voi, durante questi decenni. Probabilmente la grande chiamata che ci viene fatta dagli organismi internazionali per la transizione ecologica sarà uno stress test di proporzioni epiche per tutto il comparto ricerca, sviluppo ed educazione. Sull'educazione premetto che dovrà partire una campagna che durerà almeno 2 decenni per conseguire la cosiddetta public awareness e dovrà partire dai giovani, dai giovanissimi, dalle scuole. Non esiste, credo, la possibilità di avere una transizione ecologica di successo se non creeremo delle nuove generazioni che capiscano profondamente quello che sta succedendo alla termodinamica del pianeta, all'acqua, alla terra, la chimica di quello che mangiamo, di quello che coltiviamo, e queste cose purtroppo non si può aspettare il 20° anno di età per studiare all'università, bisogna cominciare a spiegarle in maniera semplice a 6, 7 anni, 8 anni, anche approfittando delle tecnologie digitali. Su questo ognuno di noi come genitori in primis e poi come insegnante, ognuno di voi, io purtroppo non insegno più, ma insomma può aiutare a far crescere la consapevolezza contro l'ideologia e i movimenti di chi molto facilmente ritiene di avere soluzioni immediate per problemi lunghissimi. Dal punto di vista tecnico-scientifico, quello che ho potuto constatare in questi mesi è che i problemi con cui abbiamo a che fare sono salvaguardia delle riserve idriche, dei mari, degli ecosistemi, utilizzo intelligente delle terre, rischio idrogeologico, chimica dell'atmosfera, politiche energetiche, vettori di energia, sistemi di storage, come trasformare l'energia, ovviamente chimica dell'atmosfera è anche molto importante dal punto di vista dell'azione antropica, dell'utilizzo dell'energia, tutta la chimica dei materiali che viene chiamata con un termine forbito economia circolare, ma in realtà è la chimica del materiale, la nostra Material Science and Material Chemistry. Qui ho capito che molte delle cose che io stesso pochi anni fa con alcuni di voi sviluppavo, le spugne nanotech per separare l'acqua dall'olio, certi sensori ad altissima sensibilità che erano ibridi fra biologico e inorganico, le chimiche biodegradabili per le plastiche a base di vegetali, di carta, certi sistemi di storage basati su batterie o fuel cell che utilizzavano contatti micro e nanostrutturati, chimica degli elettroliti, tutta questa roba qui che sembrava essere un divertimento di laboratorio, in realtà adesso che sono dall'altra parte della barricata sta diventando sempre più importante. Non ci sarà transizione ecologica se non ci sarà sviluppo della ricerca e dell'innovazione. Credo che questo sia un compito che dico ancora alla nostra comunità, perché spero di terminare presto questo ruolo e tornare a fare il mio mestiere, che la nostra comunità dovrà in qualche modo servire e assolvere in una maniera molto costante, dedicata, mai come in questo periodo, direi da secoli a questa parte, il ruolo degli scienziati e degli sviluppatori assume un'importanza fondamentale per il futuro, non delle prossime generazioni, ma della generazione di bambini che abbiamo adesso nelle scuole. Quindi vi auguro buon lavoro, divertitevi voi che potete, perché anche io mi divertirei molto volentieri a partecipare a una conferenza in questo momento. Spero di poter vedere alcune delle vostre cose subito applicate ai tanti problemi che arrivano su questo tavolo in questi giorni, dall'immondizia all'acqua, alla depurazione, alla chimica dell'atmosfera, come dicevo prima. Quindi conto molto su di voi e sul vostro aiuto. Buon lavoro a tutti.
Okay, so thank you all and welcome everyone. I'm Valentina Paolucci, the chairwoman of this morning section dedicated to advanced materials for sensing technologies. I just remind you that invited speakers have 15-16 minutes for their talk, followed by 3 minutes for questions. So I thank you all again and invite Professor Carlo Cantalini to give the introduction note of this section. Thank you.
Thank you, Valentina. Hopefully, I'll start with my presentation straight away. Hopefully, you will see what I have on my computer. So, good morning, everyone. The first section, Advanced Materials for Sensing Technology, actually starts with a very short introduction that I want to dedicate to the community of researchers in sensor application. Hopefully, you will allow me to start with an old picture of mine. It was shot reasonably in 1995. It was, I'm not sure if it was a summer school or a congress, but by no mistake, it was in the south of Italy. As you see, beside pioneers, I would say, of the first generation, like Professor D'Amico here, Professor Martinelli, Professoressa Carotta, Professor Giorgio Sberveglieri, as well as, let's say, Lundström here, there is also here, I would say, a second generation of scientists and researchers in the field of sensors. You may recognize here Professor Udo Weimar, Corrado Di Natale here in the middle, Pietro Siciliano, Pensa, Michele Pensa, myself, aside Professor Giorgio Sberveglieri. I believe this is a good start to inspire today's activities, which I'm going to introduce with very short 4 slides that will follow. Let's say this conference is new trends in material science, so just have a very quick look about trends in chemoresistive sensor. First of all, we cannot ignore that metal oxide currently are the base materials for chemoresistive sensor technology. They have the key point of this kind of material is their excellent chemical stability, easy fabrication, and so on. Since 2007, we had the advent of graphene sensors and its derivatives like graphene oxide, reduced graphene oxide, and with really amazing properties like no band gap, poor relative response, complex fabrication, and so on, high costs. And since 2009, hierarchical oxide nanostructures, 1D, 0D, 2D, and their combinations. As you see, the advantages of hierarchical oxide are indeed that they are open structure and I have improved response recovery times, but on the other hand, they have some drawbacks like complex fabrication, poor reproducibility from one sensor to another, and then so on. And then in 2012, 2D layered transition metal dechalcogenide, metal chalcogenides. The good point is that they are semiconductors, ultra large surface to volume ratio, good electrical properties, but as I will tell you in my presentation, the weak point of this material is the poor chemical stability. And now the hot topic. What's the hot topic? Nanoscale heterostructures, heterojunctions, interfaces, what we know as PN, double N, double P junctions with synergistic and complementary behavior. This is the hot topic of today research. So let me finish with some perspective, and let me say there is too much emphasis on remarkable properties. When we read articles in literature, there is always claims regarding excellent properties in terms of sensitivity, response time, let's say detection limits, but really very few as respect to basic understanding of the mechanisms. And there is plenty of room to this field of investigation. And as a second, the challenge for room temperature sensing and the slowness of the response time, the drift of the baseline resistance and the change of the sensor signal, what we know as sensor creep, the search for reliable, repeatable, large-scale manufacturing technologies. In this field, there is a very interesting market to be presented by electronic sensing, wearable sensor, and integration with polymeric flexible substrates to have mass market sensor to be exploited. So I would say that this is just a very quick start and introduction, and we now proceed with the presentation, and I leave my position to introduce the chairwoman of this section. Please, Valentina.
Okay, thank you, Professor, for this interesting introduction. And let's now proceed to the first invited talk of this section number 1, given by Professor Carlo Cantalini, and entitled "Controlled Oxidation of Tin Diselenide Metal Decalcogenides Toward Novel Heterostructure for Gas Sensing Application." So please, Professor Cantalini, you can start. Is the microphone? The microphone, please.
Yes.
Okay.
You will hear me now. Okay. Yes. Well, the topic of my presentation today is controlled oxidation of tin dioxide, or tin diselenide metal decalcogenides for novel two-dimensional metal oxide metal decalcogenide heterostructures for gas sensing application. A critical issue when dealing with transition metal decalcogenides is represented by their spontaneous oxidation that takes place eventually under room conditions, under laboratory conditions. This is a very this phenomenon effectively hamper the electrical response over the long run. In this picture, I've shown the high-resolution TM picture of an exfoliated tungsten disulfide, and you can see that after 3-month exposure in air, we have the onset of this heart-shaped feature that is actually a glowing tungsten trioxide over the 2D layered materials. In other words, we have the onset of an oxidation as represented here by this high resolution at high enlargement. And indeed, the structure is amorphous. Let's say that this phenomenon is thermodynamically supported, but from the kinetic point of view, it accelerates when the operating temperature of the sensor is rise to, let's say, 100 Celsius. So it's really represent a consistent drawback when dealing with this kind of material for gas sensing application. So I would say that the question is how to deal with this degradation, how to set up new passivating strategies to protect the film from further oxidation. Let me say, a possible strategy that could be a contradiction, but indeed the strategy is to simulate the oxidation by controlled oxidation to get template self-assisted, self-assembled heterostructure comprising an amorphous oxide capping layer grown over 2D crystalline flakes. In other words, to set up an amorphous metal oxide transition metal dechalcogenide heterostructure. And this can be achieved by, as I said, by controlled thermal treatment. But the point is that temperature, annealing temperature, has to be lower than the crystallization temperature of the native oxide. And then we did validation with, we demonstrated that these alpha amorphous is a self-terminating oxide. As well, we demonstrated excellent stability of the electrical properties over the long run in dry, wet air conditions. So at the end of it, we have a layered structure. Is a 2D heterostructure as shown here in this picture. We have an amorphous oxide going over the crystalline layer of the materials. And I would say that there are some advantages in this kind of technology because the amorphous skin has no grain boundaries. If we had the crystallization temperature above the crystallization temperature of the oxide, we would have grains. In this case, we have a continuous layer of the amorphous with good electrical conductivity. And the other point that could be quite interesting from the sensing properties is that we can tune the thickness of this layer, eventually matching the body length of the sensor. So we are prepared thin film sensors in this shape over high quality substrates of silicon nitrate with platinum interdigital electrodes. The thin diselenite has been exfoliated by sonication, purification, spin coating, and following the controlled oxidation in static air at 200 Celsius and for different times. It could be 1 hour, 48, and 170 hours. So we, of course, did surface chemical states were determined by X-ray photoemission spectroscopy. I go very fast now. And just to tell you that with increasing the annealing time, we have a development of almost stoichiometric thin dioxide on the surface, whereas the substoichiometric thin dioxide is reduced with increasing the annealing time. And also, as you see, the thin diselenide signal, as represented by this blue line here, where I have the pointer, disappear in the time. So we may conclude that we have thin dioxide, almost stoichiometric thin dioxide growing on the surface. And of course, we have followed the oxidation by high resolution TEM, and this is the as-exfoliated sensor with no layer on the surface. With increasing time, we have the setup of an amorphous region over the crystalline plates, which increase its thickness as according to increasing the annealing time, and eventually we have the whole surface of the 2D layer capped with an amorphous oxide layer covering the whole substrates. So the point at this stage is that we succeed to have a protective amorphous oxide layer over the 2D material, but this strategy needs to be validated by electrical properties. So we did in this direction. We did in situ annealing at 200 Celsius, and we recorded simultaneously the baseline resistance change according to the annealing time and so on. What I'm showing here is the typical test that we run to see the baseline evolution of a temperature. So the test comprises an heating from 25 to 150 Celsius and cooling back to room temperature. Films have been in situ annealed with different times and the baseline resistance recorded. The black line represents the modulation of the baseline of the as-deposited film, and as you see, the baseline is not recovered at the end of the cycle. Point B has a higher resistance, and this is the same story when if we take now the very sample at B and now we heat it up at 200 Celsius for 1 hour, and then we repeat from point C the same procedure, we see that again, at the end of this procedure, I mean after 1 hour annealing at 200 Celsius, the baseline is not yet recovered. It turns out that we need to heat for at least 48 hours and eventually 170 hours to have full reproducibility of the baseline changes and baseline reproducibility here in the starting condition as well as at room temperature. So we may conclude that we get stable electrical response after annealing at 170 Celsius. Of course, we look for the best operating temperature, and as you see, we modulated nitrogen dioxide at 1 ppm and hydrogen at 200 ppm, and as you see, the best operating temperature is here at around 100 Celsius, since we have a reasonable, acceptable, I would say, recovery of the baseline. As you see, we have no chance to work at room temperature since we have no desorption, irreversible adsorption of gases over the surface. So 100 represents the best operating temperature. And of course, we did also some electrical tests. I want just to stress this kind of procedure that we follow to assess the cross sensitivity with humidity. Well, you know, cross sensitivity has nothing to do with selectivity that we found on publications. Cross sensitivity means to see how the baseline resistance change, how the signal in terms of relative response change when two competing gases are contacting the surface of the sensor. In this first panel, we have the single response to NO2 in dry air. And as you see, we have a relative response of 2.7 As soon as humidity is put in contact with the sensor surface, we have a baseline decrease, that is attested by literature by well-known reactions, Haaland and Cole, and so on. But as you see, as soon as we have 1 ppm NO2, of course the resistance increase, but the signal increases as well. So the relative response is increased at 3.4 at respect to 2.7. At this stage, we may speculate what is the best operating the mechanisms. But of course, I would say that this is just theory. This is what we have from history, from determination. But to my opinion, we of course need more experimental to prove all this kind. But please notice that we haven't increased the relative response with humidity. That is not the same with hydrogen. We have 2.7, the relative resistance in dry air, and this relative resistance decrease with hydrogen in the presence of humidity. So it's quite intriguing that we have an increase of the sensor signal with oxidizing, and we have a decrease of the relative response with reducing gases. This can be seen in the full scale in these two plots. We have the calibrating plot with NO2, with increasing NO2 at different relative humidities. As you see, following the arrow, we have an increase of the relative response with increasing relative humidity for NO2, and on the other hand, we have a decrease of the relative response with increasing the humidity with oxidizing gases. So we had the chance to monitor the electrical response for a very long period of time. Here I show you the reproducibility tests in nitrogen dioxide and hydrogen to pulse and cumulative increase of the gas concentration. As you see, we have a very good repeatability in terms of recovery of the baseline. And the last picture here on the right represents the long-term stability over a period of 52 weeks, I mean 1 year. And as you see, we have recorded the values of the baseline as well as the values of the resistance at saturation with NO2 and H2. So I would say that we have quite interesting results in this way. These are my conclusions. We get a thermal treatment to achieve passivated oxides over to the transition metal dichalcogenide, and this thermal treatment has been validated. And then a template self-assembled amorphous tin dioxide, tin diselenide heterostructure with promising gas sensing application is demonstrated. And let me finish with my opinion that there is plenty of room at the bottom, as Feynman said. Basic response mechanisms deserve further investigation. There is a big chance to see what's going on with transition metal dichalcogenide, what's going on with this kind of surface, very complex indeed. I thank you all. I thank you all. Thank you.
Okay, so let's thank Professor Cantarini for interesting presentation. And now the session is open for questions. So I remind you to open your microphone and make your questions if there are any. No question? Okay, so I have one. Did you test this material for other type of gases below NO2 and hydrogen?
Yes, we did a full and comprehensive characterization with oxidizing and reducing gases.
with H2S, ammonia, and as well as we have new gases here, which seems to be quite interesting in this kind of period of COVID. And it's also quite interesting. So I would say, yes, we are running the ladder, as the American said.
Okay, so if there are no any other question, we can go to the next presentation that will be held by Professor Vincenzo Guidi from University of Ferrara, entitled Experience with an Operando System for Analysis of Surface Reactivity of Chemoresistive Metal Oxide Sensors. So I can see Professor Guidi.
Hi everyone, thank you, Miss Chairwoman. Let me share my presentation. You see that?
Not yet. Okay.
Okay.
Yes, we can see it.
Well done. So this is the title of my presentation. Let me briefly go to okay. Just to show you the composition of our group, since the photo taken and shown at the beginning of this meeting, the composition of the group has been quite renewed. It's myself who is the oldest of the group and the number of people around me. And just a brief, let me say, summary of what we do at our laboratory. We normally study semiconductors for as functional material for gas sensing. We study metal oxide, metal non-oxide semiconductor, organic, inorganic oxide, 2D materials. We also develop substrate and are very concerned with application, in particular environmental application, agri-food application, and medical diagnosis of colorectal cancer. We founded a spin-off based on this last application. Just a few words about the outline of my presentation. I will try to review the very basic of Fourier transform infrared spectroscopy, and I will introduce our newly operating operando system, which is a sort of powerful tool to assist the execution of measurements in chemical sensors. This is very important because it allows one to monitor the absorbed species of surface while measuring its functionality as a sensor. So it's quite important because, as differently from other operandi system working in the field of chemical sensors, it may work on a real device. You don't need to prepare quite large substrate onto which you deposit your films for characterization by operando. Just a few words about the geography of operando system around the world. The first was probably built in Kyushu University in Japan, which was followed by 2 universities in Germany, and we arrived at last with our newly developed operandi system in Ferrara. Very brief of what is concerned about the Fourier transform infrared spectroscopy. So infrared radiation is a part of the electromagnetic spectrum. So you can see it spans from the near infrared range, which is across the 10 to the 14 hertz, and then you have the middle infrared, the so-called MIR, which is what we will use for operation, and then it degrades down to the terahertz region, the far infrared spectrum. So the operando system, which we will use, is about the absorption in the vibrational states of molecules. You can see that the electromagnetic transitions are maybe divided into 3 families. The first is the electronic transition, which is like in the visible or even UV, and the vibrational states are in the infrared, and then you have the rotational down to the microwave range. So just an example, if a water molecule is absorbed at the surface of a metal oxide layer, for example, you can detect its presence by accessing the vibration. So the spectroscopy of vibration gives you an insight in what is the fingerprint of the molecule which are absorbed on the surface. Very briefly, a Fourier transform infrared spectrometer consists of a source, infrared source. We have the option to use the near infrared source or the near range. We normally use the near for alignment and the near to detect the vibration of molecules. Then you have microsome interferometer, which allows to scan the frequency of the which is irradiated to the sample, and then you have a detection system. This is quite important because you have to do all these operations on vacuum. And we resorted to an operando drift because we have, first of all, a small surface, which is the surface of the sensor itself, and also this surface is quite rough. So you have diffuse radiation, which must be captured by a proper detection. Everything must be done under vacuum except for this area all around the sensor, which is fluxed by gas, heated, and you can see later it can even be illuminated. Of course, in order to match all of these characteristics in a very compact structure, we needed to adapt what we have from the factory which sold the operand, the Fourier transform for spectrometer into a detector. This is what we have done here, all around here. Seems it doesn't. One moment. Okay. Here is the mechanical design. You can see how the sensor units can be housed, and you have the system to let the gas in and out, and we have a micro positioning system in order to allow precise alignment with the electromagnetic infrared radiation. Everything must be closed. You can see this dome. You have the window to access the light to get in, and for the infrared radiation, which is reflected and captured by a detector. And everything is done, all the rest is done under vacuum. This is because you have to avoid the absorption by water and CO2 molecules. Of course, some small part of this molecule are in the atmosphere all around the sensor, but if steady condition can be maintained, this will build up just the background and will not be a problem. Just in order to do it, we put some care to determine the flux of the gas which is fed in the chamber. You can see this is a simulation which was a representation to have a steady flux, and in order to avoid turbulence which would build up the noise. So we rebuilt the concept about the chamber, because the chamber, if you can forget about the FTIR measurement, but the chamber itself is it's very compact. It allows direct measurement of temperature, power consumption of the heater. We can measure precisely the humidity. We can set an automatic method to determine the current voltage characteristic, like we've done here in the figure. And also we have implemented a system in order to measure the current versus temperature characteristic, which is quite important to build up a Arrhenius plot, which can be in turn be useful to determine the height of the barrier into barrier. So everything is integrated into a chamber. Of course, it has only one sensor, but it is really high performing. And then we can use it with the operandi system. Just to give you some hint of how it worked, the first experiment we have done was a replica of what some other people have done in the literature. You can see here the response of a tin dioxide film, and then you feed in hydrogen, so the resistance drops down and get a steady state. And then we stop the flux, and slowly the signal recovers the baseline. So the first window you see here as dashed line is the interval which we acquired the reference spectrum, which is shown here in this picture on the right-hand side. You can see some peaks, some of which are related to isolated OH group, some other because of the breached OH group, and here you can see some deformation which are given by the OH group as a result of the bond to the tin oxide oxygen bond just beneath the surface. So what we acquire is the you can see here. And then we acquire another spectrum, which is not shown in the figure, but we can calculate the absorbance. So we get the signal when the gas is fed, divided by the signal chamber background. So the red line which I got, the called logarithm is what we call absorbance. So you can see here some picture here. Here is the exactly what people have achieved in the past in the literature, because feeding of hydrogen makes the chemical reaction to foam water, which is later absorbed. I could comment about what is the meaning of this part, but there is no time to go into such deep detail. So this is what we have done in basics. We could reply what people have done in the past, but we have done it on a real working system. So a system which is as small as a real sensor. No need to allow deposition over other substrates. This is another application, and this is in situ oxidation of a silicon carbide nanoparticles. In the past, we demonstrated that at relatively high temperature, silicon carbide, which apparently should be a very inert material, it detects sulfur dioxide at a relatively high temperature. It does it above 500 degrees C. So we made a cycle of oxidation at temperature even higher. You can see what we have done, and simultaneously we recorded the spectra of the operando. You can see that the surface of silicon carbide start to oxidize. You can see here the peak of silicon and oxygen with oxygen, and again here silicon bridge with oxygen, and then silicon again, and also silicon oxycarbide peaks. So what we understood from this study is the sensors start being effective once it's covered by a tiny layer of oxygen. So oxygen is important in the mechanism of the functionability of the sensor. You can see here, this is quite important, some peaks of the CO2. CO2 is formed as a result of oxidation of oxygen, and you can see, of carbon. You can see that it's trapped in the porosity of the sample, and it can be detected. This is another sign that about the oxidation which is taking place. So we just fed some SO2 into the test chamber and operated at relatively high temperature, 700 degrees C. So this is the signal background. The signal background is this is what we have achieved here in this red curve, which was used as a background. And so we fed SO2 in wet and dry condition. You can see the dry condition is this red curve we can see here, and the wet one is the blue one. So what is important is that you can see the spectrum which we have taken, this figure with the red or reddish and yellowish ones is about the dry condition. There's no significant oxidation in that, but it builds up a very neat peak once some water, even a low amount, some 8% relative humidity, is fed in the chamber. It means that water, the humidity, enhances the silicon, the oxide peak, and it means it stimulates oxidation. So in other hand, we demonstrated that at the surface of the nanograin, of the silicon carbide nanograin, you have some crust containing oxygen, whose formation is stimulated by water. And we also demonstrated that this accumulation of sulfur is not reversible. So we still have to understand why the sensor is reversible from the electrical point of view, and it's not reversible in terms of its chemical composition at surface. Okay, let me go further. There's no time to discuss about other development. Just to give you a hint, we integrated our operando system with an optical fiber, which can be driven by an external LED. It means that we can photoactivate our sample, so we can make important study about thermal activation, as I've already showed you in previous slides, but we can also photoactivate and make study. And another adds is we designed and constructed a cup in which you can put some powders and study the powders more than the film. So these are quite important tools which allows one to get more important information about the functionability, and everything is related to the understanding of the mechanism behind the functionability of gas sensors. So this is in summary what we can do, and of course we are open for collaboration. Whoever may be interested in our facility can contact me. We like to have established collaboration with our group, and this is a sort of facility which will be given to the Italian community working on chemical sensors. So thank you very much for your attention. I'm glad to take your question, if any.
Okay, so let's thank Professor Vincenzo Guidi for the interesting talk, and sessions now open for questions if there are any. So switch on your microphone or raise the hand.
Yes, I have a question to Vincenzo. It's a very quite interesting systems, really flexible. I've seen that you can range to up to very high temperature, and you have lots of facilities. I saw that you also have photo activation. That means that you can tune light at different wavelengths. That's a question. And then a second question is how long it takes to have a spectrum, to acquire a spectrum?
Yes, thank you. I can go up with my presentation here. It was shown in a. Unfortunately, I have some problems to in this to change the. Okay, one moment. So the duration is of about some 10 minutes. So it means you take some 10 minutes to acquire full spectrum. Okay. So potentially we could make the electronic faster and the detector system faster in order to determine even the transient. This is another plan which another extension which we are working at. At the moment, we are more concerned to the study of steady states. So before feeding gaze and after feeding gaze.
Yeah.
This is what we can observe. About the temperature, we can ride at very high level, and also we can do it as focused on very small substrate. The working area which we need to operate is 1 millimeter square, which is really unique feature. This is the only system which can work on real sensors and not only on specifically designed wide films which are more constructed in order to adapt the film to the FTIR operando system and not vice versa. So if you have any sensor, we can put in and study it. So it's quite flexible.
Yeah, that would be great for collaboration, of course.
Yeah, of course.
Thank you.
You're welcome.
Okay, so we can thank Professor Guidi for his talk, and we can now proceed to the next invited talk entitled Metal Oxide Nano and Heterostructure for Chemical Sensing, that will be given by Professoressa Elisabetta Comini from University of Brescia.
Thank you
Welcome.
for your nice introduction, and good morning to everybody. During this talk, I will present you the work that we are doing at the Sensor Laboratory, which is in Brescia University. So after talking about metal oxides and chemical sensor, I will show you some of the preparation procedure that we are using at the Sensor Lab, and then we will talk about how to improve sensing properties. And then I will try to draw some conclusion. So first of all, chemical sensors are devices, chemical gas sensors are devices that have a receptor function and a transduction function. And so what we normally do is trying to use and prepare different materials, in particular metal oxides, that change their resistance as a function of the environment in which they are put. So here you can see the sensor, how it looks after the preparation that we are doing. So we are putting our sensing material on the top of alumina substrate and then putting contacts on the top and a heater on the back. And we are going to measure the conductance as a function of time. Metal oxides are well known for chemical sensors, and we can see here most of the used materials, so tin dioxide by far, and then we have zinc oxide, tin dioxide, tungsten oxide. And just a few of them, a few studies in literature concern P-type materials. So copper oxide, nickel oxide, cobalt oxide, and chromium oxide. They are interesting because they can be prepared in very easy using very easy technologies, and they are stable over time, but they are also having properties of changing their resistance, their conductance as a function of the atmosphere. However, there are many challenges concerning this kind of chemical sensor that are selectivity, stability, high operating temperatures that are normally required for having reliable sensing signal, high resistivity, and also one problem that sometimes is not well addressed is the possibility to have large-scale production and their reliability, as we have, as already Carlo has shown you before. So what we can do to improve sensing properties? We can work, I mean, from the side of the material science, let's say, we can work on using doping, addition, on using catalysts on the top of our materials, functionalization, and also heterostructures. During my talk, I will present you the result that we have achieved on nanowires and on heterostructures. Why are we interested in nanowires? They have well-defined crystal orientation. They can be single crystalline, and therefore they can be stable over long-term operation, and they have high surface to volume ratio. Furthermore, we have nano-size dimension, at least in one dimension. Why are we going to look also on heterostructures? So on heterostructure, we have a combination of different materials in a form that can be the one in the picture you can see here. And we can have surface enhancement. We can exploit the presence of two different oxide materials. We can have charge carrier separation and can have also an increased accessibility of the cases. At the sensor lab, we are working using different preparation techniques. So we are working on the vapor phase and on the liquid phase. On the vapor phase, we are using vapor transport tubular furnace systems, and also vacuum chamber for the evaporation and thermal oxidation. On the part of the liquid phase, we are performing hydrothermal techniques and also electrochemical analyzation. During this presentation, I will just show you the conventional vapor phase with a tubular furnace. And in a later talk in the afternoon or from the sensor lab, you will see the thermal oxidation procedure. So let's see how the system is working. So we have a tubular furnace in which we have a powder in the middle and the substrate in a low temperature region. This furnace is kept at the pressure of low vacuum, depending on the material that you have to test, and we are using mass flow of argon to ease the mass transport from the source to the substrate. We can use two different grow mechanisms, so VLS, vapor liquid solid, or VS. In the VLS system, that is the one that we mostly use, we use metal catalyst for the growth. So on the substrate, we have the catalyst that can be a noble metal or the metal that is composing the metal oxide itself. when you find the right condition of pressure, of temperature difference from the substrate to the source to the substrate, you can grow nanowires instead of film covering the substrate. So it's really something that you need to study for each material. We can see here a few results concerning zinc oxide nanowires, in which I have you can see the difference on the morphology depending on the catalyst that we are using for inducing the one-dimensional growth. So the catalyst is really changing the morphology of the system. And we can see that gold for zinc oxide, but also for many other materials, is one of the best catalysts. And you can achieve nanowires or even nanorods depending on the temperature of the substrate in the system. I wanted to show you also some results on tungsten oxide. We will see some single oxide, and then we will see the heterostructure combining this oxide, these single oxides. So for tungsten oxide nanowires, you can see here the morphology, the nanowires morphology prepared with gold catalyst, and the substrate temperature is relatively low compared to other material, which is almost 500 degrees C. And we can see that the dimension, the lateral diameter of the nanowires is very small, from 10 to 15 nanometers. And the structure of the tungsten oxide that we achieve is a monocrystalline phase of tungsten oxide. And we can see here in the XRD spectra also the signal of the gold of the catalyst itself. What about P-type materials? We were able to achieve nickel oxide nanowires. In the case of nickel oxide, the evaporation temperature is very high, 1,400 degrees C, which is almost the limit of our system. But at relatively high temperature, 930 degrees C, we can achieve nanowires. Why are we interested in P-type material? Because if we want to achieve a hetero P and hetero junction, then we need also the P-type material. And the structure in this case of nickel oxide nanowires is the Bunsen-Liter structure of crystalline structure of nickel oxide. Another P-type material that we were able to prepare lately is the bismuth oxide, alpha bismuth oxide. And here we can see that in this case the nanowires are a little bit bigger compared to the other materials, and we can see here gold at the top of the nanowire. The structure is the pure alpha phase, and we can see here the peak of gold, which is the catalyst that is still at the top of the nanowires. So we have seen single oxide nanowires, and now we'll see how we can test them, but I will show you just the result of bismuth oxide, and then we'll go to the heterostructure, which is the main important point of this talk. So we are bonding the substrate, put them on a case, and put in our electrical measurement system. The working principle has already been discussed. So we are looking at the variation of the resistance or the conductance due to the interaction of the oxygen first, and then the gases, the target chemical compound that we are inserting in the test chamber. We can see here the resistance, the conductance, sorry, is a function of time as ethanol and acetone are introduced in the test chamber where we have alpha bismuth oxide. And we can see here that as we are expecting, the conductance is decreasing as a function of the introduction of volatile organic compounds. And we can see that we have a dependence on the temperature of the response. We can see here but we have almost a peak around 350 degrees C for these volatile organic compounds, while we have pretty the calibration is following the power law known for the metal oxide Benzol. We can see how the response is changing when we are changing relative humidity. So we have a small variation when we change the humidity from 50 to 90%. And we can also see how the response changes when we are changing the chemical compound that interacts with bismuth oxide. And we can see here that the bismuth oxide is almost selective to volatile organic compound, and it's not changing its resistance when we are introducing relatively high concentration of NO2, hydrogen, and CO and ammonia. So let's now start with heterostructure. We have different possibility of having heterostructure. The first is branched heterostructure. And in this case, what we are doing is doing a first deposition with a furnace with the core oxide, and in this case is nickel oxide. And then we are changing the system, and we are doing a second deposition on the top of the first one. What happens is that, and you can see here the flow of this kind of growth. In the case of nickel oxide, zinc oxide heterostructure, we have an epitaxial growth of zinc oxide on the top of nickel oxide. And we have both single crystalline materials. And if we have a look at the functional characterization, what we can see is that the nickel oxide sensor, of course, has a p-type behavior. So as we introduce ethanol and acetone, we have a decrease in the conductance, while the heterostructure sensor has an n-type behavior. So we increase the conductance as we introduce acetone and ethanol. We can see that heterostructure performs better compared to nickel oxide sensor. And we can see here that we have a very high response when we are working at 400 degrees C. So we have also change in the spectra of the response over temperature. We have tried also with other materials using the same nickel oxide as a core material. And in the case of tungsten oxide, here we can see that we have a different growth. You can see that the morphology is very different. And we have also the formation of ternary materials, so a nickel tungstenate phase in between the two oxides, with two binary oxides. The function of the conductometric response is also really different, because we can see that the nickel oxide sensor is p-type, and also the heterostructured one behaves as a p-type material. We have the highest response for ethanol and acetone at 400 degrees C, like the other heterostructure, and the response is higher compared to nickel oxide, bare nickel oxide sensor. We have estimated a detection limit of 0.5 and 0.7 ppm for ethanol and acetone, respectively. We can also change the shape of our heterostructure, so we can think about core shell heterostructure. And this, we can do it, we were able to do it in collaboration with the Humboldt University of Berlin, the group of Nicola Pina, who was putting a thin layer of nickel oxide on the top of our tin dioxide nanowires. And he was using atomic layer deposition, so we have a uniform, as you can see here, coverage of tin dioxide. But what is happening when we add this layer with different thickness of nickel oxide layer on the top of our tin dioxide? We can see here, so the dark one is tin dioxide, and then we have increasing thicknesses of nickel oxides, and we can see that the conductance is decreasing as we are increasing the thickness of nickel oxide layer, and also the response becomes different response pattern compared to the bare tin dioxide sample. What we have seen is that we have a very high response to hydrogen, and this is very interesting because we are, let's say, changing the response spectrum of the material, which is the one of the way that we can tackle the challenge of selectivity, of non-selectivity, let's say, of most of all metal oxides material. So to conclude, I hope that I was able to show that different materials have different performances and different also response spectra to different chemical compounds. Maybe we didn't have too much time to go in detail, but the morphology is really influencing the sensing performances. But not only the morphology, even preparation methods. So whatever happens during the growth of our oxides, it may change the response of the sensors made with this material. So this is why it's really crucial to study in deep the preparation procedure and their relation with the functional performances. And gas sensing devices prepared employing metal oxide, single metal oxide, exhibit high performances, but normally heterostructures made combining different materials or with different functionalization that we didn't have the time to see are increasing the response spectra, or I mean, at least changing the performances in terms of sensitivity and selectivity. And so I really believe that chemical sensor technology is really something that we need to create a new lifestyle and compatible with sustainable society. So metal oxides are one of the most promising class of sensing materials, also thanks to the easiness of fabrication methods and their chemical stability. And they were one of the first to be commercialized in form of thick films for conductometric chemical sensor, and I hope they will be part of the future also. I want to thank the project that have been founding this activity, and also you for your attention. Thank you very much.
Thank you, Professor Sacomini, for your interesting presentation. So now we are open for questions, if any. Okay, I have one.
I have a question. I have a question, Valentina, to Elisabetta. I've seen that the position temperatures are quite high in some cases. I'm wondering, is there any influence of the substrate and the electrodes when you're depositing this kind of materials?
Okay, yes, I mean, with this deposition procedure that I have shown, the temperature are, I mean, let's say, the lowest maybe 400 degrees C, starting from 400 to 900 degrees C. The fact is that we are using aluminum substrate and we are using blank substrate. So we are putting all the contacts after the deposition at the top of the nanowires and also heaters. So we have an influence of a substrate, of course, because it changes if we are using alumina, which is a rough substrate, or if we are using, I don't know, quartz, sapphire, or other substrate that may have a relatively raw roughness. So yes, I mean, roughness of a substrate, crystallinity of a substrate influences the morphology that we can achieve. Normally, when we are, and this is one of the main reasons that we are using VLS, is that when you use the catalyst, we reduce a little bit the influence of the roughness of a substrate, because the growth seed for the one-dimensional growth is the catalyst itself.
Okay, thank you. Thank you.
Okay, thank you all. And now it's time for presentation of Professor Giovanni Neri from University of Messina. I don't know if he's online. Okay. The presentation will be entitled Precise and Conformal Deposition of Metal Oxide Layer by Atomic Layer Deposition on Carbon Nanotubes for Gas Sensing Modulation. So thank you, Professor Neri.
Okay. Good morning, everybody. I would like first to thanks very much Professor Cantalini and all the organizing committee for inviting me to be a speaker of this conference. Now, you see my presentation now?
Not yet. We cannot see the shared screen.
The share. Now?
No. Yes.
No?
It's working.
Perfect.
Thank you.
Now is better. Thanks. Okay, my presentation is now on the precise and conformal deposition of a metal oxide layer by atomic layer deposition on carbon nanotube for gas sensing modulation. Okay, this part is just the continuation of the last slide of Elisabetta. We have to work in this field from a long time, collaborating with Professor Nicola Pinnazzo. But just before to start my presentation, let me to present myself. I am Giovanni Neri, professor of chemistry at the University of Messina, Department of Engineering. Messina is located in Sicily, okay, and is in the beautiful scenario of the Messina Strait, and is also visited by many visitors along the year, especially also to appreciate much the Sicilian food. Of course, cannolo and granita are very well in all the world for this aspect. Okay, just my little introduction to these fields of gas sensor, of course. Okay, why gas sensor? Conduttometric gas sensor, especially. They are a very simple device, have excellent sensitivity, low cost, of course, and small size. So we have the possibility to be integrated with the most common integrated circuits. Are used in very important industrial process, in the automotive, now also in medical and other condition. But the core of this device is the sensing layer. Sensing layer, now you see there are many different nanomaterials just in order to increase the performance, and in effect this aspect is very important today. Okay, in this field we have to start about 20 years ago in order to have many investigation about this chemical aspect, because the interaction with the sensing layer, then the chemical part with the electronic part is play a very important role in this aspect. In this field we have synthesized novel electrostructure composed of metal oxide, different metal oxide with different thickness shell into carbon nanotubes. This aspect is important in order to have metal oxide carbon nanotubes composites. We used in collaboration with Professor pin atomic layer position, because this allows you to have very precise thickness shell of metal oxide on carbon nanotubes. Of course, we have evaluated the response of these sensors at different target gases. We used acetone, ethanol, hydrogen, NO2, and so on. Evaluate the sensing mechanism of this. Also, we added here some first results regarding B-layer, where we have two different metal oxide deposited on carbon nanotubes. And at last, also to discuss the sensing mechanism. The sensing mechanism is just really on the modulation of the whole accumulation region in the metal oxide shell layer as an effect of the interaction of the target gas with the last metal oxide layer. Okay, why this moment metal oxide carbon nanotubes composite? This combination is known from long time, of course. Carbon nanotubes have important properties which are of good opportunity for the gas sensing, or also in the combination with other materials. Carbon nanotubes have a high surface to volume ratio, have a high conductivity. Metal oxide generally are instead insulating or materials, and then it is necessary this aspect, for example, in order to decrease the resistance of the materials. Mechanical stability of this material is also high, so we have one aspect regarding the stability of the deposited layer. Then, in this case, is carbon nanotubes, single carbon nanotubes, rather also multi-wall carbon nanotubes, are used in the past also for dispensing and stabilizing metal and metal oxide nanoparticles, or mixing of them. But these have just some limitation. Some limitation is related to the fact we have not one uniform distribution of these nanomaterials on the carbon nanotubes. It's possible to have also different thickness, and in this case is not one ideal sensing material, especially for studying the sensing mechanism, where well-controlled lead nanostructure are also needs. Okay? So in this case we have prepared modified metal oxide carbon nanotubes composite, having the deposition of metal oxide layer by atomic layer deposition. Okay? In this case it's possible to coat the carbon nanotubes by very thin metal oxide shell layer. You can see here just one picture of this and 10 micrograph, one these carbon nanotubes, where we can see at the external of the nanotubes wall the very fine and precise deposited layer of metal oxide. Of course, it's possible through this technique to deposit virtually any metal oxide, and one important aspect is the possibility to deposit very, very thin at monolayer. In this case, we see the experimental, the deposition of this metal oxide was performed at Humboldt University in the lab of Professor Nicola Pinna, which is an expert in the preparation of metal oxide by atomic layer deposition. The atomic layer deposition consists of different steps. It's important the film growth, differently from the other physical deposition of metal oxide, is self-limited. Then it's possible step by step to grow monolayer by monolayer the metal oxide on the carbon nanotubes. And in this case, the control of the thickness of metal oxide on the carbon nanotubes is very precise with respect to the other physical techniques we know. One important aspect that to discuss here is the classical atomic layer deposition needs necessary one post-treatment high temperature in order to form the metal oxide. Because generally in the classical atomic layer deposition we have deposition of hydrox metal oxide and not the metal oxide. We have modified just this technique in order to deposit without any post-processing treatment at high temperature the deposition of metal oxide network directly in the atomic layer deposition process. This go through the non-aqueous salt gel chemistry, and the oxygen provided in the previous atomic layer deposition from water, in this case, is provided by the precursor or organic solvent. We have studied in the past. Here you can see some publication in this aspect, and just now in the last year used this chemistry process for adding in the atomic layer deposition and prepare just one large number of these metal oxide carbon nanotubes composites. Now, sorry, you can see here, the step, the different step in the example, the preparation of titanium dioxide carbon nanotubes. The first step is carbon nanotubes functional injection. We can see later as this is a critical aspect. It's not possible to use carbon nanotubes as received, but it is necessary to have just some activity on the carbon nanotubes walls in order to have the first point of attach for the next step. Generally, in this case, we used one functionalization by nitric acid. In the second step, we have the interlayer deposition of titanium precursor. In this case, this is the first step, and the other step is the layer growth in order to increase the number of layer. This sequence, the overreaction 1 and 2 occurring on the surface of the carbon nanotubes, okay, can be repeated many times, and in this case we have the growth of the metal oxide, in this case titanium oxide. Anytime we have just repeated step 3. Important, there are some aspects regarding this atomic layer deposition. The deposition, you can see one same image on the right, is very conformal. Very conformal because the deposition is very precise, is self-limiting, okay, and then we have a complete control of the thickness. Here you can see two different carbon nanotubes covered by, in this case, I think is vanadium oxide. It's possible to see the coat of wall of carbon nanotubes from 2 nanometer to 10 nanometer. It's very simple, but important also another aspect. Another aspect is both the internal and external nanotube walls are coated. The carbon nanotube are open, and then the diffusion of gas are also permitted inside the pore of along the channel of the carbon nanotubes. It's possible to have just the deposit inside the carbon nanotubes. On the right you can see just one carbon nanotubes, okay, inside this part covered by metal oxide, and this part is one part having in the carbon nanotubes, okay, just this part is ruptured the carbon nanotubes, and inside we have the core of the carbon. You will not see it, of course, in the SEM, but is very precise this aspect. Now important is to use just this composite for gas sensing. Gas sensing, we have developed one device, planar, okay, where by screen printing or other deposition techniques we deposit small metal oxide carbon nanotubes as a sensing layer. This is just the system where it's possible to control flow of gas, humidity, and by analyze just the response we have. Important, we have different composites, metal oxide change. We have the same carbon nanotubes. In this case, we used the most simple carbon nanotube, single wall carbon nanotubes, and also used the combination of two metal oxide. In this case, we used one insulating material, aluminum oxide, but it's possible to use a combination of two different metal oxide. The first results, okay. Important, there are the electrical properties, of course, because through the exact control of the thickness, it's possible to modulate the baseline resistance. Titanium oxide, simple titanium oxide, is very insulating materials, but when you have just this deposited on carbon nanotubes, it's possible to decrease just this baseline resistance Okay, and this baseline resistance is a function of the cycle number of atomic layer deposition, and of course this depends on the thickness. More thickness, okay, is higher is the baseline resistance. Another aspect to have in consideration is the treatment of the carbon nanotube before the deposition. Why this? Because this influences very strongly the morphology of the deposited metal oxide layer. You can see here two examples. Just one example on the left, you can see very precise deposition layer. Okay, now island C in this, and we have just one precise response to NO2 with an increase of the resistance. In the other case, we have another typology of treatment, and the formation of tin dioxide is not layer, but in the form of island on the carbon nanotubes, and the response to the NO2 is completely different. And this is very important just in order to homogenize the sensing properties we need, but also indicate this technique is very versatile and possible, okay, to have a different situation anytime you desire. Also, we have just different sensing property, of course. When you have pure carbon nanotubes, in this case, this material we have as a p-type semiconductor, the response to NO2 is low compared when you have the metal oxide, in this case vanadium dioxide or pentoxide, and in the case of pure carbon nanotubes, we have a decrease of the resistance, indicate a p-type semiconductor. When we have very thin vanadium oxide coated, we have a change of the semiconductor behavior. In this case, the behavior to NO2 is as N-type semiconductor, because of course the interaction with NO2 with the sensing materials is related to the surface, and on surface we have only vanadium oxide. Okay. Important, we have a very good results about this, especially these materials exhibit high response and good signal stability. This aspect, of course, is needs when we have to develop this sensor for practical application. But probably the most important results is related to the aspect of the change of sensing properties with the thickness of the metal oxide on carbon nanotubes. We have two different typology: titanium oxide on carbon nanotubes and nickel oxide on carbon nanotubes. There are also two different target cases. In one case NO2, in the other case we have acetone and ethanol, but the response is exactly the same. The trend is the same. Initially we have one increase of the response arrived at one maximum, then a decrease in both cases. And this is important because we can suggest this is related to the fact at the optimal response we have one correspondence with the bilets. is well known when we have just the thickness at this optimal debye length. All the grain are completely devoid by electron. In this case, okay, by the most accepted sensing mechanism, it's possible all the materials participate to the sensing mechanism, and then we have a very high performance in this at this point as expected here in the sea. This just can be one schematic visualization of the formation of this heterojunction, and in this case the formation and also the height of energy barrier is related to different chemical and physical properties of these nanocomposites. Then the layer, of course, thickness, okay, the composition, the different metal oxide we can use, and the other characteristic. And this aspect is very important in order to modulate the sensing characteristic we expected of these materials. Important is the aspect you use bilayer heterostructure. In this case, the example is related to one intermediate layer which is insulating as alumina. In this case, it's possible to see the properties do not change because the intermediate layer not having any particular interaction between the metal oxide from one side, the carbon nanotube from the other side, not participate to the sensing mechanism. In fact, we have the same behavior. Of course, is completely different when we have as intermediate layer one other metal oxide having PORN type semiconducting behavior, because in this case the interaction is very strong. It is possible to modulate, as you can see recently, not only the sensitivity but the aspect of selectivity. You know, the selectivity of these materials is just not good because metal oxide respond to many gases. In this case, probably it's possible to modulate better also the selectivity. Also, Professor S. Comini just remarked in his previous presentation. Okay,
Giovanni, you would excuse me, you have just 1 minute left, please.
Okay, perfect. I finished, Carlo. The sensing mechanism comparison, because this aspect is very interesting, we can see just when we have carbon nanotubes, the interaction between nickel oxide and carbon nanotubes is very high. It's possible to modulate the different resistance. In the case when we have semiconducting materials, insulating material, aluminum oxide, the aspect is more simple. In effect, do not change with respect to nickel oxide. Change when you have another semiconducting material. For example, we used tin dioxide or zinc oxide. Okay, just this final mark just discussed in the previously. We have a homogeneous conformal metal oxide layer. It's possible to optimize metal oxide shell thickness and have electronic coupling. And of course, probably the best way to operate is also to modulate and change the different metal oxide. Just special thanks, of course, to Professor Pinna and his PhD students at Humboldt University, Razza, and my PhD students, Kove Muller, and thank to you for your kind attention. Thanks very much.
So thank you, Professor Neri, for interesting presentation. Now, if there are any questions.
Yeah.
I have a very quick one, very quick question. Giovanni, you showed us the tin dioxide grown of carbon nanotubes. My question is probably an easy point, but is it amorphous or crystalline, the tin dioxide grown over carbon nanotubes?
No, this layer is amorphous.
Is amorphous
because just depend on the preparation. The preparation used is a very low temperature using the organic layer deposition, and then is not necessary to have. But in case it's possible to increase the temperature in order to obtain crystalline, nanocrystalline deposit. It's very simple to change. Okay.
Yeah, very first, the last. Is it porous? Is it porous tin dioxide, or is very thick and?
Depend on the, of course, the nature of the metal oxide. Depend on the pretreatment of the carbon nanotubes, of course, because it's possible in order to have a porous to have a different active seeds. Okay, depend on the thickness. At very low thickness, we have an island, okay, but increasing, when increase the thickness, the film is continuous, okay, and the porosity depends also the final treatment if you have, of course. There are many possibilities. This atomic layer deposition is very versatile in order to obtain very large different nanomaterials.
Thank you. Thank you.
Okay, so thank you all, and let's have 30 minutes only virtual coffee break, unfortunately, and we'll start again at 11:30, sorry.
Thank you, Valentina.
Thank you.
See you later.
Bye.
See you later. Okay, welcome back again for this second part of morning session of Advanced Material for Sensing Technologies. So next presentation will be given by Professoressa Simonetta Capone from CNR AMM from Lecce, and will be entitled Human Volatilome, a New Challenge for Gas Sensors-Based Electronic Nose. So we can share the contribution, and then we will have question times.
Thank you, Mr. Chair. Today I will introduce you to the new topic of human volatilome that represents a new challenging application field for gas sensors. I will give a survey of application example from my working group at CNR EMM in Lecce. The interest in human volatilome starts with breath analysis as the frontier of non-invasive diagnostics. Hundreds of volatile organic compounds, both inhaled and exhaled, are present in breath at very low concentration as a result of gas exchanges at blood cell and alveoli blood interfaces. As a consequence of what occurs inside body, Vox in breath represent in some way a dynamic fingerprint of the healthy status of an individual. Vox are present not only in breath but in all body fluids as blood, urine, saliva, skin, feces, etc. They are produced by metabolic activities taking place in the body. Such circulating metabolites can provide early insight into developing disease states because they reflect and magnify the perturbation at lower genomic, transcriptomic and proteomic levels several thousand-fold. Moreover, metabolites provide information about actual disease activity in contrast to genomics, which only provide the starting point, is the counterpart of genomics. VOX can hence be used as a disease biomarker for early detection and screening, diagnostics, precision medicine, including patient stratification for therapy selection and treatment monitoring. All the VOX arising from human body constitute the human volatilome. That is a powerful source of information not only on metabolic processes, but also on the exposure of a subject to a multitude of external factors as ambient, lifestyle, diet, microbiome, drugs, etc. The PET of environmental VOX in the human body is a complex process of mixing, diffusion, distribution between blood, adipose tissue and other physiological fluids, as well as of metabolic activities. The rate and degree of elimination of environmental VOX from the body depend on the concentration of the compound, the duration of exposure, the solubility in blood and lipid tissue, and in the individual physiology. Since gas sensors have sensing properties also toward VOX, they can give a fundamental contribute to volatilome analysis. The human volatilome is hence to be considered as a part of the exposome concept. In 2005, Wild coined the term exposome. Exposome encompasses lifetime environmental exposure that include lifestyle factors from the prenatal period onwards. Later, in 2010, Rappaport and Smith refined the approach to emphasizing the role of the chemistry in the organism and defining the exposome as the totality of human exposure from all exogenous and endogenous sources in what we can call internal chemical environment. This latter definition takes into account the exposure, not only the exposure of chemicals entering the body from the environment, from as contaminant, ambient contaminant, or via food chain, or as with the use of consumer products, but also include compounds produced in the body by inflammation, oxidative stress, lipid peroxidation, infection, microbiome, and all other natural processes. This joint exposure can be related to adverse health effects via exposome-wide association study. Without attempting to identify mechanistic causes as in the traditional adverse outcome pathway approach based on classical ecotoxicology. However, in an holistic vision, a synergy between the two approaches will be the key for a better health risk assessment. And in this vision, biomarkers have a fundamental role, since they may represent key events leading to adverse outcome, but also events that are without direct relevance to the adverse effect, for example, representing a compensatory reaction. So, untargeting approach is useful to discover unknown biomarkers. Our interest as a group focuses on volatile biomarker, what is known as a volatilome, that is part of a metabolome, trying to understand their specific contribute together to other omic science to disease risk. Human volatilome has two main application fields, human biomonitoring and clinical application. The first include exposomic study for assessing population-wide exposure to hazardous chemicals, with a particular interest in population living in contaminated areas. The second include disease screening, diagnostic, prognosis, and monitoring for follow-up. Both research areas of exposome and diagnostic stimulate our more comprehension in health risk assessment and disease mechanism, and offer a new and exciting challenge for sensor field. In literature, gas sensors were more used in diagnostic, while up to now, biomonitoring is not a fully explored application field for sensors. At the gas sensor lab of CNR-EMM in Lecce, we are active both in breath analysis and volatilomics. We sample the box in different biofluids, breath, urine, blood, from sample population for case control studies. And we were also the first group who characterized the volatile fraction of human semen. We also carry out basic studies on VOX produced by cellular cultures. We use two different methodologies for volatilome analysis. One based on gas chromatography mass spectroscopy with the solid phase extraction as extraction method for VOC of the VOC in the sample id space. The other is based on electronic devices constituted by gas sensor array. We developed a compact electronic nose that provides as output patterns of sensor responses for a volatilome data analysis. Human volatilome is hence really a challenge for gas sensors, both for human biomonitoring and diagnostic application. In our lab, we work to develop a gas sensing device supporting the training of the device with gas chromatography GCMS analysis. Of course, multivariate statistical analysis and pathway analysis are also performed to extract the information from the data. I'd like to show you a recent biomonitoring study that recruited the young men living in Land of Fires and Valley of Sacco River, two known highly contaminated areas in Italy due to illegal waste. We sample semen, urine and blood from these guys. The results allowed us to evaluate the distribution of the identified VOX in the three considered biofluids. Several VOX were found statistically significant for discriminating the two areas. As an example, we plot the 3-methylbutanal that was present in higher concentration in human semen and the Venn diagram. The PLS-DA allowed to separate the two areas as a consequence of the exposure to the two differently contaminated areas. The best results were obtained considering all the three biofluids. Their aerial secures confirmed such results and gave a detailed analysis considering all the combination of variables and biofluids. The same samples were analyzed by a Fourier sensors array. Here we see the results of the principal component analysis for blood samples. Valley of Sacco River group is concentrated while Land of Fires seems spread around it. However, performing a linear discriminant analysis which even discrete a fair discrimination as a result from the confusion matrix. A better discrimination was get with the quadratic discriminant analysis, as expected for the sensor's behavior. Moreover, we get interesting results from multiple linear regression, building a model between sensor responses and VOX molecules. We are able to predict with an high determination coefficient R the VOX concentration on the base of the sensor responses. Here a list of the estimated VOX in the three considered biofluids. And a survey of the predicted versus observed VOX concentration for seminal liquid and blood, again VOX estimation in blood. Of course, for each of these compounds, we could discuss a lot about its significance and the biological pathway that leads to their presence in the biofluid. And here, but in urine, we can see here the regression results. Okay. By using a multiple linear regression model on sensor responses and seminogram, we surprisingly note a very good estimation of seminogram parameters, cell concentration, progressive motility and motility percentage. A minor prediction was get for the total motility due to the contribute of non-progressive motility, but this was also expected. And here you can see our electronic nose. We developed a flexible electronic nose that we named Spirox for human volatilomics application. Spirox is able to analyze the responses of a semiconductor metal oxide array to the Vox complex of any air samples collected in a Tedlar bag. So, for example, a breath sample, as well as any liquid or solid biosample collected in the id space of a suitable vial with a gas type septum. Here you can see the architecture of the device. And the system, for the system hardware, we choose to uncouple the main board from the electronic board of sensor. In fact, we have a main board. It is an advanced platform complete with all the functions necessary for the electronic nose, and then sensor module with 6 gas microsensors. We developed, of course, firmware and software. We use Spirox in a project where we explored the urinary volatile biomarkers of prostate cancer. Thanks to the Istituto Superiore di Sanità, that gave us access to its biobank, we analyzed the urine samples from controls and subjects with prostatic cancer. From PSA plots, we can see the data structure and a first difference between the two groups. The LDA, linear discriminant analysis based on the responses of the sensors, device sensors, showed a fair discrimination between the two classes with good accuracy, sensitivity, and specificity. The complementary analysis by GCMS identified hundreds of Vox and selected those, 27, that are significant for the discrimination among the two groups. Some of them are down-regulated, while other groups are up-regulated. And you can understand the rich information that is contained in this data. The discriminant analysis performed by both PLSDA and LDA gave also satisfactory results regarding the classification between the two groups, control versus prostatic cancer. Another example that we like to mention in relation to breath analysis was the development of a smart breath analyzer based on different gas sensors for exhaled oxygen, carbon dioxide, and Vox. We developed it within the project Respiro for the telemonitoring of exhaled breath in patients suffering chronic respiratory failure and home assisted by mechanical ventilation. We arrived at high TRL, setting the device at the patient bed in hospital. We are excited about the perspective of such studies and confident in the new knowledge that can be acquired through them. We have different ongoing studies. We mention an exploratory clinical study on patients suffering Alzheimer. This study was carried out in collaboration with the Hospital of Lecce. And also a new biomonitoring study that will recruit residents in Land of Fires, an high contaminated area, and in Valle of Sele, a lowly contaminated area. The project was in collaboration with the Eco-Food Fertility Project and will start from next November. It will recruit both men and women. It will be the extension of our study. And we have also founded the project for Frightis, the name, where we will collaborate with Bari Hospital. We will analyze the volatilome in chronic renal disease patient that has a higher risk of mild cognitive impairment. And so we will use, of course, the combined analysis by nose and GCMS. And our aim will be the disease MRC stratification, as well as the biomarker discovery for correlation between the two pathologies. We have also studies on the box released by Cellular Culture in collaboration with another institute of CNR in lecture, and we published also some results. I'm finished, and I like to thank you for your attention, and also all the members of the Volatilomic group at my institute. Thank you again.
Okay, so let's thank Professoressa Capone for her nice talk.
Thank you.
If there are any questions, we are open for questions. Okay.
I have a question. That's really quite interesting research, and I would say very sophisticated one, since it needs validation on a medical basis. I'm wondering, at which stage of research you are. I mean, did you manufacture a prototype? Is it this prototype on service in somewhere in hospitals or things like that?
Allora, yes, we develop a prototype. The prototype we call Spirox. Of course, it was not certificate or other. This prototype that is based on commercial sensors, we choose these sensors just to look forward a commercial application, but at the moment we develop one prototype that we use in laboratory, but just because we analyzed in the laboratory the samples that we received from our collaborators.
So it's still in the development phase, actually.
Yes, it's in development phase. It reached a good TRL, and since we can produce other of these, as we are thinking to do, since we have maybe more collaboration and some collaboration, some studies has to go together. So we are planning to do more of this prototype.
Yes. May I ask you the last question? Are you manufacturing the metal oxides by yourself, or you buy metal oxides for your
yes.
minerals?
Yes, in our laboratory, of course, we are able to develop both materials and platform for sensors, so to produce our own sensors. But we decide to use commercial sensors in this prototype in order to have a more reproducible ability, to have just thinking to some application, repetitive application, and to have the same sensors without, some limit of
course.
Just for this, yeah. It was while for the other sensors that we use for COPD patient, we use in the telemedicine system. It was the results of a now closed project. And we use also their commercial sensors together, MOX sensors, commercial MOX sensors with electrochemical oxygen sensors and carbon dioxide infrared sensors, the two gases in the breath. And we use in the hospital with the collaboration with the doctor, because it was there was some problem in doing in the home of the patients, while for certification and safety reason.
Okay, thank you so much.
Okay, let's thank Professor Capone for her interesting talk, and now let's go to the second invited talk of this session that will be given by Professor Alessandro Martucci from University of Padova. And the talk will be entitled Bio-Inspired Bragg Reflector Made of Titanate Nanocomposite as a Platform for Humidity Sensors. So I can already see Professor Martucci. We can start the presentation.
Thank you, Valentina. I will try to share my presentation here. Okay. Okay, good. So I'm going to talk about a multi-layer film that we prepare for humidity sensing, trying inspiration by nature. I will show you in a moment. So before showing you the sensor, just a few words regarding the materials that we are using. So we use silk fibrin, which is a protein extracted from silkworm fiber, and this has good mechanical properties. It is biocompatible and biodegradable, and it is possible to process this solution is water-based solution in which you have dispersed the protein in different ways, and you can dope, and then you can deposit by spin coating, and you can process also with soft lithography, nanoimprinting, inkjet printing, stenciling, and also contact printing. And indeed, Professor Omeneto showed the possibility to develop different type of optical devices based on pure silk. But for many applications, you need to control the refractive index of your material, including silk. So we try to do this, including some nanoparticles that we developed, and these nanoparticles are titanate nanosheets. So titanate nanosheets are a layered structure composed by titanium oxide sheets, and in between the sheets there are different type of ions, tetramethyl ammonium ions, and also water. And they are pretty small. The size range between 5 to 10 nanometers, and we can have from 3 to 10 stacks. And this could be UV curable, and it's possible to do also ion exchange, and during the curing it's possible to remove the tetramethyl ammonium ions between the layers. So we combine these titanate nanosheets dispersed in water with the silk solution dispersed in water, and we could get our nanocomposite solution, and this we can deposit by spin coating or drop casting, inkjet printing, and then we can cure in different ways: methanol curing, temperature curing, UV curing, or doing ion exchange. So this is a TM picture of titanates inside silk matrix, and this is a close look of one of these titanate nanosheets, and you can see 6 layers. You can also appreciate the very small distance between the layers. So we could prepare both membranes, freestand film containing different content of titanates, and this freestanding film can be made flexible with simple hydration and in water, and by changing the content of titanates and also the type of curing, we can tune the refractive index in the visible from 1.55 to almost 2. And as I said, we could process this film in different way: E-beam lithography, UV lithography, and inkjet printing. So coming to device that we developed, we were inspired by a beetle that lives in desert, and the skin, the cuticula, change color depending on the humidity. And this cuticula is made by several layers, and this layer have a low and high refractive index. And when the humidity change, both refractive index and thickness of the layer change, so this causes a change in the reflection. And so we try to replicate this structure using our silk and silk titanate nanocomposite. So we deposit our multi-layer structure, okay, that is made by silk. So this is pure silk, so a low refractive index, and this in blue is the high refractive index silk containing the titanates. And we did a little bit of optimization in order to get the proper thickness and the proper refractive index of both pure silk and high refractive index silk. And using this thickness and this refractive index, we could get a brass peak centered in the visible. And with only 4 couples of bilayer, we could really get our peak in the visible, as said, centered around 400 nanometers, and keeping a good transparency of our multi-layer deposited on glass substrate. So here you can also appreciate different layers in these SEM images. So we prepare this multi-layer deposited on glass or silicon, and then we check both transmission spectra and also reflectance spectra by changing the relative humidity. And here are the results. So this is the Bragg peak that shift by shifting the relative humidity, and this is reversible. And indeed, we also check hysteresis, which is very important in the case of humidity sensor. And as you can see here, the hysteresis was pretty low. And then we checked also the stability, and we switched from low humidity to high humidity, and checking that we could really recover our signal, and we can reproduce our variation of transmittance at a certain wavelength. And at the same time, we also tested the long-term stability over roughly 4 months, and the stability of the signal, so where the position of our Bragg peak at 10% or 80% was pretty stable over this period of time. So we also try to understand the sensing mechanism. We did a little bit of simulation, and we measured also the refractive index of the 2 different layers at 10% humidity and 80% humidity. And as expected, we have a variation of thickness, due to water absorption or desorption, which correspond as swelling or deswelling. So when we increase the refractive index, both the pure silk and silk titanate, the thickness increase. At the same time, the refractive index decreases. This because we have uptake or loss of water molecule. And this, we have a strong effect in the case of titanate due to the presence of the titanate. And this is in accordance with the simulation. So let me see if I can run this video. Maybe not. Sometimes it works, sometimes not. Let me see. Maybe, yeah. So this is an example. You can see it's very fast response when we blow over this sensor, and it is quite fast, both the response and the recovery, as you can appreciate. So let me conclude. So in conclusion, we synthesize a high refractive index silk titanate nanocomposite. We can tune the refractive index up to almost 2, and we could process our composite in different ways, and we could in particular prepare silk multilayer with a peak in the visible, which is very sensitive to humidity. And so in this way we could make a good sensor with good reproducibility and stability over time. So thank you very much for your attention, and I will be happy to get questions from you.
Thank you, Professor Martucci, for your interesting presentation. And if there are any questions, we are open, or in case.
Yeah.
In case
As usual, I have a question for Professor Martucci. Very amazing, quite interesting. It is amazing to mimicking from nature some basic principles. I have a question. You know, there is a very emphasis about electronic sensing, wearable devices for monitoring body, humidity, things like that. The question is, do you think this multi-layer could be integrated over flexible substrates, I mean polymeric or things like that?
Yeah, indeed, the idea to use silk was really from one side to have a biocompatible material, and from the other side, as I show you, you can make a very flexible membrane. The trick is the right hydration in the case of silk, in combination with the curing. Because if you, let's say, crystallize too much the silk, it gets very fragile. So it's you know, a trick. You need the right process in order to have the right flexibility.
Okay.
And for sure, silk is biocompatible, and already Professor Omeneto developed some devices to be implanted in body.
Thank you, Alessandro. Very interesting.
Thank you. If there are no any questions, we can proceed to the next invited talk of the session that will be given by Professor Corrado Di Natale from University of Roma Tor Vergata. I hope he is online. I can see him. Okay. Title of presentation will be Gas Sensors Based on Organic and Inorganic Hybrid Nanostructures, the Porphyrins in Oxide Case. So you can share your screen. And...
Share my screen.
Okay, thank you.
So you can see. Do you see my screen?
Yes.
Okay. Yes. Okay. Good morning, and thanks everybody thanks to the chairwoman for the presentation and to the organizers of this event for inviting me. And today I will give you some, let's say, overview about our work in developing organic and inorganic nanostructures for gas sensing. And when I talk about organic, I will talk about porphyrins. Let me give you some very simple introduction to sensors. It's not just to start again, but just because this vision is in some sense instrumental for the development that we are doing. We know that the sensors are electronics devices. So from the point of view of the electronics, they are something that can be connected in a board, and they transform. Then they give meaning to the electric signals, and these meanings is just given by the interaction with the volatile compounds in case of gas sensors. So there are volatile compounds interacting onto a sensitive material. Some property of this sensitive material changes, and what we do with the sensor is just to measure the change of this physical property that is affected by the interaction. So there are a very large number of possible sensitive materials, but a limited number of kinds of transducers that can be applied. As I said before, we are, let's say, working in Tor Vergata since many years with my colleague Roberto Paolesse, who's a chemist, and he's, let's say, he synthesizes and design porphyrins. And porphyrins are very well known in biology because some fundamental functions in life are carried out by porphyrins. For instance, they carry oxygen in the blood, or are the active element in the light harvesting and energy transform in chlorophyll, or they even activate electron transport and catalysis in cell, in a class of proteins called cytochromes. So they are very interesting from the connection between electric properties and chemistry and the capability to bind molecules. So there is a larger use of porphyrins in technology, for solar cells, for even for in medicine, for photodynamic therapy, or any molecular electronics too. But we, of course, have been interested to develop sensors and gas sensor in particular. And the first things that we can see about porphyrins is that porphyrins can bind the different molecules. In this little cartoon, we can see the interaction with the methanol, with the benzene. So molecules that are different in character can bind onto a porphyrin. So a porphyrin is a sort of a multiple binding system where different interaction mechanisms can occur: hydrogen bond, acceptor and donor, hydrophobic interaction, aromatic interaction. And since a metal is usually present in the porphyrin core, the coordination to the metal is also a very important additive interaction. So it is then possible to make sensors with porphyrins, but we have to take into account this complexity of interactions. So in the past, we just studied many different kinds of sensors, And the most effective, let's say, to consider all these interaction without giving, let's say, privilege to one of them is to use the Quartz Microbalances, which is, or in any case, mass sensors, which is a very straightforward way to make a chemical sensors, because it just weighs the amount of molecules that are absorbed by the sensitive material. As a drawback, of course, mass, any molecules has its own mass, and then this measurement is absolutely specific. So this means that when we coat with a quartz microbalance the surface of a quartz microbalance with a film of porphyrins, what we get is a sensitive sensor, but absolutely unselective. This is the response of one of these quartzes, and you see that there are responses to many different compounds and a very large range of concentrations, because the different, let's say, saturation pressure of the volatile compounds, but you see that you cannot say what are you measuring here, because from the single signal of a single sensor you cannot derive you cannot, let's say, infer the nature of the volatile compounds. But we know that this can be obtained by an array. So instead of considering one sensor, we consider a number of sensors, but each sensor has to be differently selective. So they have individually non-sensitive, but the sensitivity to the different compound is different. So we need a method to make from a single porphyrin, let's say, a family of porphyrins differently behaving. And a very simple way of doing this is, for instance, is to change the metal coordinated in the porphyrin pocket. So when this happens, of course, the combinatorial selectivity of the array gives the possibility to identify each individual compound. So what cannot be obtained with one sensor can be obtained by the array. And we know that this is the principle of electronic noses, because this behavior is the behavior chosen by nature to, let's say, give to the animals the perception, the chemical perception of the surrounding environment. So a limited number of receptors, but each receptor senses more molecule, and each molecule is sensed by more receptors. So the only way that we need to do in technology is to make arrays of sensors that are non-selective, but differently selective. And in the past, let's say, we just used the porphyrins-coated quartz microbalance just to assemble sensors and to make electronic noses. These electronic noses have been used in different applications, food quality, or even, let's say, to control the quality of the air inside the spacecraft, or very important, as been discussed before by Simona Capone, the medical diagnosis. With these sensors, we provide the first evidence in 2003 that lung cancer can be detected from the breath. And then this has been applied to many different diseases, not least the COVID-19. Now, the idea now was just to go ahead, to move from the quartz microbalance in order to get, let's say, resistive sensors. It's not strictly necessary in terms of chemical reaction and application, but it is interesting in terms of development, because the resistance is the most simple, let's say, electronic devices. So all the electronics then becomes much more simple. And there are many ways to make conductive sensors with non-conductive sensitive materials. For instance, we can exploit charge transfer or surface charge, let's say, in this sensitive material when they are deposited on two semiconductors, such as carbon nanotubes or silicon nanowires. Or even, this is also a nice, interesting alternative, let's say, to take conductive particles, carbon black or metals, and to coat these particles with sensitive materials, and we get a material where current moves, let's say, jumps by tunneling between each particle, and this tunneling depends, the barrier between the particles depends on the chemistry between them. So any absorption changes the the conductivity of the device. So many of these can be, let's say, followed. In the past, we made something of this, for instance, porphyrins onto carbon nanotubes, or mixtures between porphyrins and tin oxide. This was done with a group of Siciliano in Lecce. But more recently, we just, well, in the last, let's say, 15 years, actually, we just moved to a different consideration. So the fact that porphyrins can actually be used in light harvesting systems. So this is the very well-known story of the dye-sensitized solar cells, where a wide bandgap semiconductor, such as titanium oxide or zinc oxide or whatever, are coated with a molecule that is a good absorber of visible light. And then, due to the correspondence between molecular orbital levels and conduction and valence bands in the semiconductor, the photo-excited electron can be injected into the conduction band and then can increase the conductivity of the semiconductor. In a dye solar cell, this circuit is closed by an electrolyte here, but we were interested to the semicell, so to this, let's say, structure, where we have a dye coating a metal oxide semiconductor. So this is just the situation. So when we have porphyrin, for instance, onto zinc oxide, under light, porphyrins absorb light, photoexcitation of the electron jumps in the conduction band, and then we have a change of conductivity of the zinc oxide. But at the same time, this process changes the interaction between, let's say, volatile compounds and the porphyrin, and it makes more easy the charge transfer from the volatile compound to the porphyrin, and the light is a sort of a pump that brings electron from the porphyrin into the zinc oxide. So we just exploited this, let's say, studied this idea, let's say, a few years ago, about 10 years ago, and just making nanorods coated with the porphyrins. And what we got was just the results just shown the photoconductivity. So the system is sensitive to the visible light, and visible light is because of the porphyrin. These are the spectra of the zinc, and this is the absorption spectra of the porphyrin. Using a white LED, you just excite only the porphyrin. So this is just the photoconductivity, but at the same time, we also found a very short increase of the response to electron donor systems, molecules, for instance, triethylamine. So this concept has been, let's say, developed then a little bit. For instance, how to prepare the material. In this case, we just grow the nanorods with the nitrothermal method, and then porphyrins are applied by casting. And this is one way, or one, let's say, route to prepare, for instance, even nanoparticles. So we can just take nanoparticles by the hydrothermal method, and then to add porphyrin in solution, and then we wait in order to get the deposition of porphyrins onto the zinc oxide nanoparticles. For the scope, the porphyrin is properly functionalized with the carboxyl group. But a different way is just to put everything together, so make a sort of one-pot synthesis where porphyrins are added to the precursor of zinc oxide, and then they grow, in some sense, together. What we get is that this is the very good, let's say, pure zinc oxide nanoparticle. When it is deposited with porphyrin, you see the crust of porphyrin at the surface, but when you have the one pot, the very well regular shape is almost lost. So we get, let's say, but in terms of sensors, we have something that can work. And then these porphyrins can be then from the solution be, let's say, drop casted onto array into, let's say, the standard interdigital electrodes onto substrate in order to get an array. This is an example, one of the last example where we compared two families of macrocycles, porphyrins and corol. Corol is a cognate molecules. See, is missing one of these methane bridges. There is a direct connection between these pyrols. So just let's say made a comparison between free base porphyrin corrol and copper porphyrin, copper complex of porphyrin and corrol. The resulting film onto the let's say onto the substrate is a multiple, let's say, grains, so we have current jumping from one grain to the other, and in this passage there is a barrier made by the presence of porphyrin, so we expect that the presence of porphyrins affect, and corrode affect the conductivity. This is just a picture of this system, only for sensors. In an open, let's say, with a window, an optical visible light window in order to illuminate the devices. And then these are the responses to families of different volatile compounds, representative of different, let's say, molecule, different families of chemistry. It's interesting to see that the resistance increase always, except two noteworthy cases, triethylamine and triethylphosphate. These two molecules are known to be good, let's say, to coordinate to the system, to the microcycle, and even to be electron donor. So in this case, there is an effective electron donor to the porphyrin, and then we have an increase of conductivity, then the resistance decreases. In the other cases, the molecules are absorbed and they form an additional barrier between grains, and then we just see the increase of resistance. Of course, this is an array, so we can, let's say, make a principal component analysis, but what is interesting is that we have not the largest sensitivity to amines, but we have a signature for amines, because for amines and triethylphosphate, we have a negative sensitivity. The sensitivity in general is still ruled by the totality of the interaction. So, for instance, van der Waals interaction are very efficient, still very efficient. So we have that large alcohol like butanol can, let's say, be absorbed and so on. But nonetheless, we have a very clear signature of the presence of the amines because the response is negative. And it is also interesting when we compare this stuff, when we do these studies, to distinguish between the concentration, the quality from the quantity. And I said that these compounds, let's say, have been measured at different fraction of the saturated pressure. So this value in terms of ppm is highly variable. So we may have, let's say, here a very dense, let's say, they are packing the different, let's say, data are quite overlapped. But anyway, it's possible to distinguish, only few of them. For instance, this is water, these are butanol and detanol, this is butylamine, here there is triethylamine, this is triethylphosphate, because of the effect of the concentration that is highly variable. We can remove, or better, we can, let's say, mitigate the influence of concentration just with the linear normalization. It means to divide the response of each sensor by the sum of the responses of all the sensors. This corresponds to reduce to length 1, to norm 1, the multivariate response of the array. And then we can take a principal component analysis. What is interesting here is that actually when we make this kind of normalization on our data, since we have negative response, the data spans a circle. You remember that the normalization just means to reduce to length 1 the response, and then all the data spans a spherical multivariate sphere surface. And since we have negative response, the sphere is just complete. So when the principal component analysis is applied to this configuration of data, we can get, let's say, errors, because these data are projected together. And this is just something that limit the capability to recognize the different compounds. But recently, Spherical Pca has been introduced for this scope. So instead of applying the principal component analysis to the Euclidean coordinates, it is applied to the rotation than to the angles. And in this case, when it is done, let's say the recognition of the different compounds is quite absolute, except for alcohols that are still plotted overlapped. And here the negative response, triethylamine and triethylphosphate, are quite well separated from the rest of the compounds. So this kind of maps gives a sort of olfactory atlases, because they are very similar, not the same, because these are cells, so these are, let's say, real signals, while this is just a software image. But it is just gives, let's say, an approximation of the olfactory bulb, where different families of chemicals are, let's say, plotted, or better, appears the signals from different region of the olfactory bulb. And then this atlas can also be used to infer what happens to unknown compounds. For instance, these are compounds due to fish spoiling meat, and spoiling meat, you have a path going towards a mine, and these are the wine, and wines are currently between alcohols and the water. So just the last minute, just let me go back to the quartz microbalance, because this let's say binding of molecules onto the zinc oxide nanoparticle changes the arrangement of the molecules. So, and this is very important in a sensor, because the arrangement of the porphyrin has to ensure the fact that the volatile compounds can interact with all porphyrins. And in this case, we just made a quartz microbalance, but with just the porphyrin, and the porphyrins onto these two, with these two methods of growth with the zinc oxide. So after the formation of the nanoparticle and the one-pot nanoparticle. And what we get is that the same porphyrin, but it is in three different geometrical arrangement, and it is enough to give different selectivity to identify different compounds, and also to identify complex compounds, such as, for instance, the volatile compounds from cultured cells. And finally, this arrangement on nanoparticles is also very efficient to preserve the enantioselectivity in molecules. Porphyrins can be synthesized, for instance, with this proline group, in order to give capability to recognize enantiomers. And if we want to preserve this property in a sensor, we have to prepare the sensor in order to not to destroy this property. So all the molecules have to be arranged in order that this chiral center can effectively interact with the volatile compound. And this is obtained with when the molecules is binded onto zinc oxide nanoparticle, and then these nanoparticles are used to coat the surface of the quartz microbalance. In other cases, when this is directly, let's say, deposited, either amorphous or aggregates or porphyrins, the differences between enantiomers does not appear, but it appears, let's say, when the porphyrins are onto the nanoparticles. And this is just, again, what I said right now. So to conclude, I say that organic chemistry is of great importance for make chemical sensors, because of the great versatility, the large number of possible molecules or possible materials that can be designed, prepared, synthesized, and used. But we have also to couple this with the proper sensor, and the nanoparticle, let's say the binding of molecules onto nanoparticles is an interesting method, let's say, to provide conductivity, and so to make, let's say, resistive sensors, but also to arrange the molecules into a structure that can preserve most of the sensitive material selectivity. Okay? So this was my presentation, and thank you for your attention. Okay.
Thank you, Professor Di Natale. So if there are any questions, you can ask.
Yes, a very quick question to Corrado. I've seen that it's a very quite sophisticated structure that can be even activated by light, visible light, and so on. I'm wondering about the data acquisition and data validation. You use multi-component analysis. Just a simple question: how long it takes to deconvolute and to have data analysis to have a result?
Well, there are two steps: the training and the use. Just those called the test. But when you routinely use your model, in training you just assess your model, and for that you need data. You need, let's say, to accumulate data. So this depends, of course, on the application. In a medical application, there are several, and you know, you are just this is quite common to many, let's say, different aspects of sensors. Let's say that if we have, for instance, if we want, for instance, to discriminate between two in a pathology, for instance, lung cancer, non-lung cancer, but we know that people are not characterized only by lung cancer or non-lung cancer. There is a lot of additive variables, and if we have to include them in the model, this means to measure a large number of population. But once the model is trained, the calculus is absolutely immediate. So
it's a self-learning model.
The model is self-learning, but it is labeled. I mean, you train the model. You have to say, okay, these are the patients, these are the control, and these are those with this variation of the disease, and so on. So you have classes, and then you learn, you teach the algorithm to discriminate among these classes. And then once this is done, you know, then it's very fast. And thermocalculus is very fast.
Yeah, thank you. Thank you, Corrado. Thank you.
Okay. Can I stop sharing?
Yeah, you can stop. Valentina, please, the volume. Valentina, you missed the volume.
Okay, sorry. Okay, so we can go straight to the last presentation of this morning session that will be given by Professor Jean-Marc Tugliani from Politecnico di Torino, and will be entitled "Food Wastes as Raw Materials for Humidity Sensing." So we can share the presentation.
Yeah, okay, registered.
Yes, sure. Okay. Just a moment. We have some technical issues.
Valentina, scegli tutta la schermata.
Good morning to everybody. Today I will illustrate you how we use two different kinds of food waste for the preparation of humidity sensing materials. This work was done in collaboration between Politecnico di Torino in Italy and the Kyoto Institute of Technology in Japan. First of all, why is it still interesting to study humidity sensors? Well, if we think to quality control of production and products in various industries, and if we think to automatic control systems, and also if we imagine humidity sensors that have to work in extreme conditions such as high temperatures and corrosive atmospheres, well, at that point there is still a demand, and this demand is growing throughout time for this kind of sensors. So we decided to investigate new humidity sensors prepared from two different kinds of food waste, just because food production, food processing, marketing, consumption and disposal have an important environmental impact because of energy and natural resources use, and also because of embedded greenhouse gas emissions. So in our case, we used coffee powder because each year more than 11 billion tons of coffee are consumed, and used coffee usually ends up in landfills as municipal solid waste. Then the second waste we use is rice husk. Rice is the most consumed food in several countries, and again each year more than 1 billion tons of rice husk is produced. So let's see now how we processed these raw materials for the preparation of the sensing materials. First of all, let's start with coffee powder. After we drank our coffee at the bar at the university, we recovered the powder, which was washed several times by means of distilled water. Then it was dried and pyrolyzed at 700 degrees for 1 hour under nitrogen. At that point, we recovered what is called waste coffee biochar. This powder was ground in order to be compatible with the screen printing process we used for the production of sensors. For rice husk, the situation was a little bit different because we didn't use directly rice husk, but we used rice husk ash that was provided by a company close to Torino, which is called Hydroblins. This company uses rice husk for the production of energy, so we recovered the ash. This ash, as you can see, is quite big in size, and it is full of carbon. So at that point, this product was fired at 500 degrees for 3 hours to remove, if not completely, at least the main part of the residual carbon present in the material. It was then manually ground and finally sieved in order to be compatible with the screen printing process, as I said before, and then we recovered the rice husk ash. Then let's see the sensing materials characterizations. First of all, we determined the particle size distributions by means of laser granulometry. Coffee powder was quite big because the average particle size was around 33 micron, and 90% of the particles were below 215 micron. So this size is too big for it to be compatible for the screen printing deposition, and the powder has to be sieved. X-ray diffraction evidence that the powder was amorphous, and nitrogen absorption by means of BT technique revealed a specific surface area of 5 square meters per gram. Then for what concern rice husk ash, after sieving, as you can see this table, the mean particle size was around 23 microns, while 90% of the particles were below 44 microns after sieving. Then X-ray diffraction evidence also that this material was mainly amorphous, with a diffused peak around 22 degrees into theta, characteristic of the presence of some disordered cristobalite. Nitrogen absorption evidence slightly lower, specific surface area of about 2 square meters per gram on the powder, fired at 500 degrees for 3 hours, and then for 1 hour at 600 degrees, which is the thermal treatment that was used for the preparation of sensors. Then FESM observations evidenced for coffee biochar a porous structure, which is positive for, of course, water molecules adsorption, and the chemical analysis showed that the material was mainly composed of carbon, but a certain amount of oxygen was also detected, and also traces of phosphorus. For rice husk ash, also the observations evidenced the porous nature of the material, which is again also positive for humidity detection. Then We investigated both materials by means of Raman spectroscopy, starting from coffee biochar. The well-known DNG peak were evidence. These peaks were not, unfortunately, fitted by 2 peaks, but they were fitted by means of 4 peaks. And this is the signature of a rather disordered structure. And this was evidenced by the ratio between the 2 areas of the DNG peaks, which was close to 3. We did also the same Raman spectroscopy on rice husk ashes, and we also observed the presence of these 2 DNG peaks that were also fitted, in this case, by means of 3 peaks, which is again the signature of an almost disordered structure. This was also evidenced by means of the ID over IG peak area, and in this case the ratio was close to 2.4. Then we performed X-ray photoelectron spectroscopy on carbon on coffee biochar, and of course the disordered structures were evident when we looked at the high resolution spectrum of carbon bonding, and we evidenced sp2 carbon bonding as well as sp3. The ratio between these two peaks was close to 4. And again, this was the evidence of a certain disorder within the structure. High resolution spectrum on oxygen, 1s bonding, evidenced the presence of CO single or double bonding. XPS analysis on rice husk ash, again on the materials fired not only at 500 but also at 600 degrees, evidenced the presence of silicon but also of carbon, and traces of potassium and of phosphor were also detected. The high resolution spectrum of carbon peak evidence again the presence of sp2 and of sp3 bonding. In this case, the ratio of these 2 peaks was close to 2.7, which is anyway the evidence of a certain disorder within the structure. Then high resolution spectra of silicon and of oxygen evidence for silicon the presence of SiOX fragments by means of these SiO-Si bonding, as well as the presence of SiC bonds and SiOH bond. Finally, for what concerns the high resolution spectrum of oxygen, the presence of amorphous silica was also evidenced. Then let's see how we prepare the sensors and how we test them. We used, as I said before, the screen printing technique. So we deposited first the platinum interdigitated electrodes. These electrodes have a thickness of about 400 microns, and their distance is more or less the same, close to 450 microns. After firing of these electrodes, we deposited then the sensing materials on top of them, and you have here the picture of the sensor we prepared by means of the coffee biochar. The sensors after screen printing were fired only at 300 degrees for 1 hour for the coffee biochar sensor, while the RHA sensor was fired at 600 degrees for 1 hour. Then we investigated the response of these sensors with respect to humidity by means of lab equipment. In this case, gas cylinder bottles were connected to mass flow that were, of course, controlled by a mass flow controller. In this case, what happened is that one of the mass flow was used for generating a humid air flow, and all the others were used, on the contrary, to dilute this humid air flow in order to produce a range of humidity values ranging from 0 to almost 100% of relative humidity. The impedance of the sensor was measured throughout the experiment by means of an LCR meter. We applied a tension of 1 volt at 1 kilohertz on the sensor. Then we express the response of the sensor as the relative change in the impedance with respect to the impedance value under dry air. Both sensors showed N-type semiconductor behavior, that is to say the impedance decreased throughout the experiment when the relative humidity value increased. And for the coffee biochar sensor, the impedance decreases from 23 to 25 megaohm in dry conditions until 8 or and 12 megaohm. It depends on the sensor we tested in humid conditions. Then we observe a certain hysteresis between the absorption and desorption curve. At 74% relative humidity, the maximum hysteresis was about 15%. Then the limit of detection was about 20% relative humidity. We did the same experiments on the RHA sensor, and in this case we observe a maximum hysteresis at about 25% RH, and this maximum hysteresis was about 14%, so very close to the previous sensor. In this case, also the sensor behaved as an N-type semiconductor, and the impedance value decreased from about 19 megaohm under dry air down to 200 kilo ohm under 93% relative humidity. Then we investigated the repeatability of both sensors, and this repeatability was very good for a coffee biochar sensor. As you can see in this graph, we repeated the 3 cycles of dry air and humid air, and the curves are perfectly overimposed each other. We investigated also the response and the recovery time of these sensors. These response and recovery time were almost fast under medium relative humidity values, while these values were quite high when the relative humidity increased. At the same time, for the RHA sensor, the repeatability measurements were perfect, and in this case, the response and the recovery times were quite fast, even for high relative humidity values, on the contrary to what happened with the coffee biochar sensor. So, to conclude this presentation, new sensing materials based on coffee biochar and rice husk ash were successfully prepared. The humidity sensors exhibited an N-type semiconducting behavior in the range 5 to 100% relative humidity. The response and recovery time were rather fast, at least for up to 50% relative humidity for the coffee biochar sensor, while this response and recovery times were fast in all the investigated relative humidity values for RHA sensors. The selectivity of both sensors was excellent, specifically with respect to carbon dioxide. None of these sensors evidenced cross-sensitivity with respect to CO2. This was very positive for humidity sensors. However, we evidence for both films a certain aging. For example, after 1 year for the coffee biochar sensor, the sensor response decreased from 14% to 9% under 15% relative humidity, while for the RHA sensor, after 6 months, we evidence drastic change from 90% to 15% of the sensor response under 50% RHA. This decay quite fast for RHA sensor was probably due to the depolymerization of silica within the sensor, and this was probably due to the presence, as we have seen from XPS analysis, to the presence of K3PO4, which was detected on the surface of the material, and but was probably the cause of this depolymerization of silica. Thank you for your attention, and if you want to go deeper into these materials, you can find here the references of these two papers we have already published. Thank you once again for your attention.
Okay, so first of all, sorry for technical issues. However, I want to thank Professor Togliani for his interesting speech. I don't know if he's online. Okay, nice to see you.
Good afternoon.
If there are any questions, we have time.
Yes, as usual, a question to Jean-Marc. It's quite interesting to know that now there is a new family of humidity sensors made of coffee biochar. It's quite really interesting. I'm wondering, is there any correlation? This is a porous structure, and is there any? Did you measure pore size distribution and to get a correlation between humidity sensing?
Thank you, Carlo, and thank you also for the invitation for this presentation. No, so I am sorry, we didn't do any gas absorption measurement. We just measured the specific surface area of the powders above, but we didn't measure the pore size distribution.
I have another a very quick question, a second one. Probably I missed some point, but you mentioned the silica on the surface by XPS's analysis. Where does silica signal come from?
Well, in fact, rice husk hash is rich of silicon. So after burning it, you produce silica, and it's the main phase in the ash. After that, there is also a lot of carbon, because even after three thermal treatments, considering the one done by the company and the two we did at 500 degrees and 600 degrees, there is still some carbon present on the surface. But we were not able to identify where carbon is with respect to silica by SEM observations.
Yeah. Just allow me a last question. I am very curious, but how did it happen that you started with this material?
Well, in fact, we do many different researches in our labs, and we were working, in fact, with in cementitious materials with biochar for replacing carbon nanotubes in cements to improve their mechanical properties. And then I was the co-tutor of a PhD thesis on these materials. And then my former PhD student decided to test these materials as humidity sensors. So it was fortuity who allowed us to test these materials.
Okay. Quite interesting. Thank you, Jean-Marc. Thank you.
Thanks to you again. Thank you very much.
Thank you again for a nice speech. So morning session has come to the end. So I want to thank you for attending this session, and I want to thank all the speakers for their interesting speeches, and thank the organizers to give me the opportunity to chair these sessions. And so let's start the lunch break that will be last for 1 hour, and we'll start again for afternoon session, always on sensing technologies at 2 p.m. So see you later. Thank you all again.
Good afternoon. Here back again for the afternoon section of New Trends in Material Science and Engineering. This first day has been dedicated to materials for gas sensing applications. I will be chair the section, this afternoon section, and let me start by introducing the first talk of this afternoon. It is Professor Alessandro Longato from the University of Padova. Welcome. The title of his presentation is Soft Gel synthesis of tungsten oxide in films for hydrogen sensing based on gas chromic properties. Please, Longato.
Thank you, Professor.
The volume, you missed the volume, the microphone. Anna, you're right, you're right.
Yeah.
Please,
Okay.
go ahead.
Can you hear me? Yes? Okay.
Yes.
Thank you, but I'm not a professor, not yet. I'm a PhD student.
Not yet. Okay.
And today I would like to talk about the Sol-Gel synthesis of tungsten oxide for hydrogen sensing based on gasochromic properties. So, very briefly, hydrogen is the fuel of the future. It is, and more importantly, will be used in a number of applications, such as vehicles and fuel cells. It is a green gas, so it is very important to develop hydrogen gas sensors. But we still have a few challenges to face, such as the sensor should work in the absence of oxygen. For application in which no oxygen is present, the sensor should be reversible, so it should return to its previous state. It should be quantitative, so that it not only detects the presence of hydrogen, but also it measures it. And last but not least, it should be selective, so that it detects only hydrogen. The material I chose as a hydrogen gas sensor is tungsten oxide. Tungsten oxide alone does not interact with hydrogen. But if we use a catalyzer, such as platinum nanoparticles, then the hydrogen dissociates on the platinum nanoparticles and then is transferred to the tungsten oxide via hydrogen spillover. Here, in the tungsten oxide, hydrogen reduces tungsten from 6+ to 5+, and it changes its color from transparent to blue. Thanks to this property, we can use tungsten oxide as an optical sensor for hydrogen. The synthesis I used to make tungsten oxide is a Sol-Gel synthesis. And we start from metallic tungsten powder and hydrogen peroxide. The reaction is strongly exothermic and has to be first conducted in an ice bath, and the temperature is slowly raised up to 60 degrees Celsius. In this way, we obtain peroxide tungstic acid, which is the precursor for my tungsten oxide, and we mix this with a solvent. Then the solution is spin coated on silica glass substrates, and the film is stabilized at 120 degrees and thermal treated at 5 different temperatures: 200, 350, 550, 700, and 900 degrees Celsius. The solvent we used were 4 different solvents, and we saw that isopropanol is best, and probably due to its low surface tension. The characterization. Well, we characterized the samples with 3 different techniques: scanning electron microscopy, ellipsometry, and X-ray diffraction. In the SEM, we saw 3 different structures. Below 500 degrees, we saw no apparent morphology with a flat film. At 550 degrees, we begin to see the grain boundaries of the film. And at 700, we see an important crystalline structure. At higher temperatures, we do not see any film on the substrate. And this is also supported by the XRD measurements. In fact, below 500 degrees, we only see an amorphous structure of the tungsten oxide. Above 500 degrees, we see a crystalline structure with water peaks. And above 800 degrees, in particular at 900 degrees, we only see the silica glass substrate, so an amorphous structure. And this is only supported by the ellipsometry measurements. In fact, we see that by raising the temperature of the thermal treatment, we see a decrease in thickness, and at 900 degrees we no longer see any film present in the substrate. And the explanation for us is that there is a phase transition for the tungsten oxide at 740 degrees from an orthorhombic structure to a tetragonal structure. And we think that the tetragonal structure no longer adheres to the substrate and it detaches itself. What about the platinum? Well, very briefly, we made the platinum nanoparticles starting with a polyol synthesis, starting from platinum hexachloride. We obtained the platinum nanoparticles in ethylene glycol, and we precipitated them with acetone and redispersed them in ethanol. This solution was then spin coated on to the tungsten oxide samples. Here we can see a SEM image of the tungsten oxide sample with on top the platinum nanoparticles, and here on the left we can see the platinum nanoparticle, a time image of the platinum nanoparticles, which are about 10 nanometers in size. They are also cubic, and this is confirmed by the XRD measurements in which we see the phases 111 and 200. So, for the gas sensing, we put the samples of tungsten oxide with on top the platinum nanoparticles in this test cell, and this test cell was then put into a standard spectrophotometer. In this way, we can take simple absorption measurements of the sample of the thin films, and here we can see a typical absorption measurement of the tungsten oxide in an inert atmosphere in black, and in red the absorption spectrum of the tungsten oxide when hydrogen passes. So there is an important change in the absorbance, and dynamic measurements were taken here at 850 nanometers. Dynamic measurements were taken between air and hydrogen in argon, and between argon and hydrogen in argon. In this way, we can compare the two and see if we can work in the total absence of oxygen. The measurements were taken at room temperature, 100 degrees and 200 degrees Celsius. Here are the measurements, the dynamic measurements, but I summed up all the performances of the sample in a table, and here it is. What are the performances that I am interested in? First of all, the maximum absorption change, which is basically how much blue the sensor becomes. Then the time of coloring, that is the time in which the sensor becomes blue, the time of bleaching, which is the time in which the sensor returns transparent, and then the percentage recovered both in oxygen and in argon. And that is basically if the film returns totally transparent, 100%, or if it retains a little bit of blue. First of all, we can see that by raising the experimental temperature of the measurement, there is a general improvement on the performances, and this is to be expected. But we can also see that the amorphous film at 200 and 350 degrees show a good maximum absorption change of 0.2, but the other performances are really bad, both on time and percentages recovered. Instead, the crystalline film at 550 and 700 degrees show 100% recovery at 250 degrees of experimental temperature, which is really good because it is both in oxygen and in argon, with good time of coloring and time of bleaching. The absorbance is a little bit lower, but this is probably because the film is less thick. What about the quantitativity? Well, we took the sample heat treated at 700 degrees, and we started from 100% atmosphere of argon, and we went slowly up to 20% hydrogen in argon. And we see that the absorbance changes with the percentage of hydrogen. So we can say that the sensor not only detects hydrogen, but also it measures it. We also tested a few interferences of gases. For example, we saw that with a gas stream with water and CO2, the sample is the sensor works just fine. But with hydrogen sulfide, the sensor does not work anymore, and this is because it is well known in the literature that sulfur compounds poison the platinum catalyst. So nothing new here. So to conclude. What were the challenges that I set up at the beginning? Well, first of all, does the sensor work in the absence of oxygen? Yes, it does. Is it reversible? Yes. And this with a crystalline film treated at 550 or 700 degrees at the working temperature of 250 degrees. The sensor is quantitative, and it is selective for the few gases we've tried, but I cannot have any sulfur compounds present in the gas stream. And this is all, and thank you for your attention. If you have any question, please.
Thank you, Alessandro. Are there any questions regarding this paper? Well,
I have one, if possible.
Please.
I noticed that when you show the absorbance at different temperatures, you got a higher absorbance at 100 Celsius as compared to temperature. Could you explain this behavior?
Yes, we noticed that only for the film at 700 degrees, we see that the signal, the maximum absorption change is higher at 100 degrees than at 250, and this was quite strange. So we actually, I actually have a backup slide for this. Here it is. We saw that by raising the temperature, the maximum absorbance slowly rises up to basically 0.1, and then it decreases again. So this is quite strange. We do not have yet an explanation for this, but we also see that by raising the temperature, the performances of time of coloring and time of bleaching improves, but the maximum absorbance change decreases. Thank you for your question. Yes, it was okay. It was something that we noticed.
Okay, you answered. Thank you.
Okay. Let's move now to the next talk given by Valentina Paolucci of the University of L'Aquila. The title is Zinc Oxide in Films Containing Aliovalent Ions for NO2 Gas Sensing Activated by Visible Light. Please, Valentina.
Good afternoon, everyone. The title of my presentation is Zinc Oxide Thin Films Containing Aliovalent Ions for Nitrogen Oxide Gas Sensors Activated by Visible Light, and reports the results of a joint research activity between our group and the NanoEng group from University of Padova. Aim of this work is to enhance the sensing properties of zinc oxide by improving its low temperature performances using the activation provided by visible light instead of thermal activation. With this scope, we synthesized doped zinc oxide nanoparticles through an heat-up colloidal method, starting from zinc stearate and different precursors to obtain aluminum, gallium, silicon, and germanium doped zinc oxide with a nominal doping concentration of 5%. In general, N-doping of zinc oxide with trivalent and tetravalent ions has been always used as a strategy to enhance zinc oxide conductivity. However, the particular choice of this dopant is related to their characteristic to induce a localized surface plasmon resonance in zinc oxide in the near-infrared region, which have several advantages, and in particular, it improves the charge carrier density enhancing conductivity and making the material more sensitive to small local changes in charge density. In this slide, you can see some SEM images representative of the thin films made of zinc oxide nanoparticles. The blue square belongs to aluminum doped zinc oxide, the red one to gallium, the orange one to silicon doped zinc oxide, and the black one to germanium. They show the different final microstructure induced by doping, and as you can see, doping with trivalent ions produce spherical nanoparticles, which are quite bigger as compared to the one obtained with tetravalent doping, which have smaller diameter and an elongated shape, indicating possibly a preferential growth direction. Also, XRD was performed to assess crystallinity, and the analysis confirmed that all the samples can be indexed with Wurtzite crystalline structure, and doping does not induce any substantial modification in the diffraction patterns. Also, the calculation of crystallite size given by XRD reveals to be in line with the outcomes of SEM investigations. Here I reported the results of the XPS analysis that we have performed to investigate the surface chemical composition of the 4 films. Regarding the zinc-2p core level spectra, no substantial modification are observed between the 4 samples, and in all cases the peak belonged to zinc oxide. On the contrary, some differences can be observed in the O1s core level spectra of the differently doped sample. In particular, the convolution of the spectra identifies 2 peaks. A green peak, which belongs to the O2 minus oxygen atoms in the stoichiometric Wurtzite structure of zinc oxide, and another peak here, the blue one, which is related always to O2 minus oxygen atoms, but this time located in defective regions. So this blue peak represents actually a confirmation of the presence of defects. And the incidence of this peak is important to assess the defective structure, the defective nature of the sample. And it's worth noting that, for example, in the undoped zinc oxide, the extent of this peak is only 37%, and for doped sample, this its contribution increased from 50 to 70%. For the sake of completeness, I also reported core level XPS spectra for the different doping species, attesting the effectiveness of the dopant incorporation for all the samples. From now on, I will focus on sensing properties of our doped zinc oxide films, and here I report the investigation carried out to understand the variation of the baseline resistance with temperature. All the samples show a semiconductive behavior, modulating in a reversible way their resistance in the temperature range 25–150 Celsius and dry air atmosphere. But turning back to the motivation of this work, we performed gas sensing measurements in the presence of visible light activation of the sensors. For light-assisted gas sensing experiments, we used commercial 4 colors LED, which have been mounted directly inside the test chamber facing the sample, and the emission have been, of course, characterized. So we found that red light is centered at 630 nanometers, corresponding to 1.9 electron volt. Green light is centered at 570 nanometers, corresponding to 2.1 electron volt, and purple blue light is centered at 430 nanometers, corresponding to 2.8 electron volt. So first of all, we monitored the influence of visible light illumination at different wavelengths on the 4 doped zinc oxide film. We did these experiments for different temperature, and here I reported only 75 Celsius for brevity. As you can see, as respect to dark conditions, only purple blue light has the effect to significantly decrease sensor resistance, of course, with different extent for each material. So, given this result, we decided to monitor the effect of purple-blue light at 430 nanometers on sensor responses to 400 ppb nitrogen oxide in the temperature range 25-100 Celsius. Here the result at the lower temperatures, and the first evidence, of course, is that at room temperature, no response is observed for both doped and undoped zinc oxide, while under purple-blue light, irradiation at 25 Celsius, a slight but significant response is detected to NO2. At 50 Celsius instead, while undoped zinc oxide still gives no response to NO2, doping itself seems to be effective in improving zinc oxide performances because it induced a significant response to nitrogen oxide. However, also in this case, the gas desorption is very poor. If we now focus on the response at 50 Celsius and purple-blue light, we can observe that in this case the desorption is faster as respect to dark, meaning that recovery of the baseline is improved in the case of light illumination, and moreover relative responses are bigger under light illumination as respect to dark. Here you can see the complete panel showing also the temperatures of 75 and 100 Celsius. We can say that light always improves the responses, but its effect is clear that it's more pronounced at low temperatures as respect to the area 1, in particular at 100 Celsius. And this phenomenon can be related to the fact that thermal activation involves all the materials and not only the exposed surface, while the effect of light is limited to the surface exposed to LED. Anyway, these results assess that the best operating conditions are achieved at 75 Celsius and purple-blue 75 Celsius and purple-blue light illumination, and the best results are obtained for silicon-doped zinc oxide in terms of both relative response and recovery, as you can see from the orange signal. So I will focus on this material to give you more information about its sensing activity. Here I reported the dynamic gas response to lower NO2 concentration under both dark and light illumination. So given the experimental detection limit of 40 ppb, which is a very low concentration of nitrogen oxide, again, no illumination means poor baseline recovery after gas exposure, while the effect of light is to improve both recovery and reproducibility of the measurement. At this point, a rapid overview on sensing mechanism is important. So, zinc oxide, it is well known to be an N-type semiconductor with a band gap of around 3.3–3.4 electron volt. And it has been demonstrated that at temperature below 100 Celsius, O2 is the stable oxygen species absorbed on lattice oxygen vacancies. This phenomenon induces the formation of the depletion layer with subsequent resistance increase. When visible light is introduced with a wavelength of 430 nanometers, the associated photon energy is only 2.88 electron volts, so it is not sufficient to directly overcome band gap and interact with electrons in the conduction band. And even doping fails to modulate band gap enough, considering that the lower obtained binding energy is measured to be still 3.2 electron volt. However, it's reported that the absorption energy of an O2 molecule on zinc oxide oxygen vacancy may range 2.3–2.4 electron volt, meaning that purple-blue light provides enough energy to desorb oxygen by directing pigment, leading to oxygen desorption according to this reaction. These mechanisms also explain the absence of any resistance modulation in presence of red and green light, considering that the energy associated with that wavelength range 1.9 to 2.2 electron so it is not enough. Regarding NO2 sensing mechanism instead, we know that under dark conditions, NO2 reacts with the oxygen absorbed on oxygen vacancies according to this reaction number 3, leading to an increase of sensor resistance due to the broadening of the depletion layer generated by the substitution between oxygen and NO2 molecule, which is more electronegative. When zinc oxide film are illuminated with purple blue light, reaction 2 takes place. So vacancies are available for interaction with NO2, and we can say that reaction 4 takes place. So NO2 directly reacts with oxygen and vacancies and electron from the conduction band. So under purple blue light illumination, NO2 may react according to both reaction 3 and reaction 4. And these mechanisms also explain the bigger change on the relative responses under purple blue light, considering that the direct consumption of conduction band electrons is a likely more energetic mechanism as respect to the one claimed in reaction 3. Lastly, turning back to experimental results, for gas sensors is also important to observe the cross-sensitivity, that is, their ability to detect the target gas in presence of an interfering one, for example, water vapor. And here, water vapor at 40% relative humidity. Here again, I reported the results for silicon-doped zinc oxide. As you can see, under dark conditions, sensors exhibit no recovery of the baseline, as attested by the baseline drift associated with the black dotted lines. On the contrary, purple blue light improves recovery and reproducibility, as attested by the red and blue dotted lines. However, a slight reduction of the relative response is observed in this case, as you can see, demonstrating that nitrogen oxide and humidity compete between each other because of their interaction with oxygen vacancies. So I came to the conclusion, and I demonstrated that it's possible to yield excellent sub-ppm NO2 sensing by the combined effect of mild temperature and visible light irradiation for 5% trivalent and tetravalent doped zinc oxide films. Light activation results to slight increase sensor relative response, but has a very positive effect on desorption and baseline recovery. And finally, we demonstrated that humidity results to slightly inhibit sensor relative response to NO2 because a possibly competitive mechanism with water. So I conclude my presentation. Thank you for your attention.
Thank you, Valentina, for your presentation. So let's move to the next talk. It's Angela Malara from the Mediterranean University of Reggio Calabria, and the title is Detection of Heavy Metals by Hybrid Electrospan Polyaniline Fibers. Please.
Good afternoon. My name is Angela Malara and I am a researcher at the Mediterranean University of Reggio Calabria. In my talk, I will speak about the detection of heavy metals by hybrid electrospan polyaniline fibers. Well, I would like to start my talk with a famous quote that should make us to think about it. Someone said that we are the only species that have cropped up the planet and the only species that can clean it up. That in other words, it is to say that we have caused the problem and now we have to solve it. But it is not a simple thing when we came across one among of the biggest issue of our time, such as the contamination by heavy metals. Therefore, in this talk, I will briefly introduce an overview on the heavy metals contamination, the realization of an innovative hybrid material that could try to mitigate this problem, a material that will be realized by the electrospinning technique, and then the electrochemical measurement used for the detection of these heavy metals. Well, as I said before, heavy metals contamination is a big issue because it affects all the compartments of the environment, that is to say water, air, and soil. Although heavy metals are a natural element of the earth crust, and they are also positive to some extent to the good functioning of the human body, if their concentration overcome the limits of permission, they became harmful. Therefore, we need to detect it and to neutralize it. Although, as I said, the heavy metals are present on the earth crust, they are also produced by numerous human activities such as land manures, the use of fertilizers, of pesticides, and coal combustion, the spillage of petrochemical, and so on. Therefore, as a result, we have a wide distribution of heavy metals in the environment, and we need to find a solution because they cannot be degraded or destroyed. So we need to detect it and also to find, promote, for example, their recycling. Therefore, our attention was concentrated on the development of an innovative material that could be used in this field. Indeed, as we know, there are numerous techniques that can be exploited for the detection and quantification of heavy metals. A device that is able to detect heavy metals in a fast way, easy way, economic way, and moreover on site is still lacking. Therefore, we concentrated our attention on the development of a new material by the electrospinning technique that could be coupled with the electrochemical measurements, since currently this combination has been identified among the most attractive one. In the specific, the electrospinning technique, as everyone knows, is a method that can produce fibers from the nanometric to the micrometric dimension. Basically, the process consists in the preparation of a polymeric solution, so a polymer that is solved into a proper solvent, filled into a syringe, and then with the use of an applied high voltage, the liquid is charged, a jet is formed and elongated towards the so-called Taylor cone. And finally, fibers are deposited on the ground collector. The result of this process is the formation of a mat of a textile that is composed of a lot of fibers that can have a nanometric or micrometric dimension. The process is also simple, inexpensive, and moreover scalable. In our case, we decided to use the polyaniline conductive polymer that was first activated in camphor sulfonic acid, and then added with the polyvinyl acetate used as a copolymer in order to improve the spinability of the solution. Graphene oxide and iron oxide were also added as a dopant to the solution. Once the electrochemical parameters, the electrospinning parameters were established, we were able to obtain a self-standing mat of 3 different materials. Polyaniline with polyvinyl acetate in the same ratio, in the same weight ratio, and then the doped samples with the graphene oxide and iron oxide respectively. Materials were characterized with a complementary technique. In particular, the morphological characterization was performed with the scanning electron microscopy. In particular, as we can see from the images, fibers were randomly oriented, and the diameters were distributed in an homogeneous way. It was possible to detect also some agglomerated particles that, however, are typical of the PANI systems, as also reported in literature. The presence of the dopants elements, graphene oxide and iron oxide, was also further investigated with the energy dispersive X-ray analysis. Indeed, it was possible to highlight that these additives were distributed along the structure of the single fiber. The presence of iron oxide and graphene oxide was also confirmed by the electrical conductivity measurement. Indeed, as we can see, the electrical conductivities of the realized samples were order of magnitude lower with respect of the pure PANI. This because, obviously, for the presence of the copolymer that have a sort of dilution effect, and also for the presence of graphene oxide and iron oxide that, being positioned along the structure of the fiber, represented a point of discontinuity, and so have a detrimental effect on the electrical conductivities of the materials. An electrochemical characterization was also performed on our samples, and so it was possible to evaluate the specific capacitance by means of the equation here reported. As we can see, when the total scan rate was increased, the specific capacitance registered the decrement for all the samples in different ways. Finally, we also evaluated the equivalent circuit of our system that was used to model the experimental data obtained by the electrochemical impedance spectroscopy. Indeed, EIS measurements were performed with the electrochemical setup shown in this slide. A 3 classical electrodes configuration was used, with the working electrode realized with the electrospan membranes. Measurements were realized in aqueous solution, so ammonium acetate buffer solution was used as reference. And then when the measurements were performed in the contaminated solution, lead, cadmium, thallium and chromium were used with a concentration equal to 200 micrograms per liter. The results of the EIS measurement were finally plotted in the form of Bode and Nyquist plots. Measurements were realized first in the pure buffer solution, the so-called blank measure, and then were repeated for each contaminant, so for lead, cadmium, thallium, and chromium. The performance of the material was evaluated in terms of impedance, so the potential detection of heavy metals was evaluated by the comparison of the impedance values registered in a contaminated solution referred to the impedance value registered in the blank, in the pure buffer solution. In particular, considering the low frequency region, it was possible to highlight that in the case of the undoped sample, The different impedance values are ascribed to a slight sensitivity towards heavy metals, with the exception of chromium that was not detected at all, since its impedance value was equal to the impedance of the material in the pure buffer solution. When the doped sample were considered, indeed, we could see that in the case of the iron oxide, we could not speak neither of sensitivity, neither of selectivity, since all the impedance measurements were equal one to the other. In the other case, when graphene oxide was used, indeed, we could detect variation in the impedance values with respect to the buffer solution. So it was possible to detect all the 4 different heavy metals. Moreover, the selectivity of the material could also be tuned by choosing the working frequency at which the impedance values was maximum. Therefore, we decided to further investigate this material, the polyaniline doped graphene oxide, since we believe that it is possible to realize a sensor able to detect heavy metals through the impedance variations. In conclusion, the electrospinning technique was used to realize the 3 different hybrid materials that were characterized from a morphological, chemical, electrical, and electrochemical point of view. The electrical impedance of fibers was measured in a wide range of frequencies and in different contaminated solutions. The polyaniline doped graphene oxide sample was characterized by the higher electrochemical performances. Therefore, we believe that it will be further investigated for the development of a PANI-based sensor for the detection of heavy metals. In conclusion, I would like to thank all the co-authors of this work, and that was financed by the project Sensor, and obviously all of you for your kind attention. Thank you.
Thank you so much. If there are any questions, the section is open for questions in case. If not, I have a question. My question is about the repeatability of the response. You actually loaded particles within this map of fibers. And I'm wondering, is it stable? The particles, charged particles are stable. Does they stitch? Can they be maintained? Is there any reproducibility of these Nyquist plots?
Thank you for the question. All the experiments were repeated 3 times, so we are sure that material was all the 3 materials tested were stable in this range of time and these measurements. Obviously, when we use electrospinning added with particles, it is really very difficult to be able to reproduce the same material. So therefore, there are little variation between one mat and the other. So this should be taken into account. But with the same mat, we were able to produce big sheet of mat. We were able to reproduce the same results.
Yes, very good. The difference between repeatability and reproducibility, actually. It works like this. Very good. Thank you.
Thank you.
So let's proceed with the next talk from Ryan Zribi, the title from University of Messina, and the title is Publication on Novel Electrochemical Sensors Based on Carbon Clothes Matrix functionalized with molybdenum oxide and 2D molybdenum sulfides layers for riboflavin determination. Please.
Hello, everybody. I am Rehan Zribi from Tunisia, and I am a second-year PhD student at the University of Messina, Italy, at the engineering department under the supervision of Professor Giovanni Neri, and I am associate researcher at the CNR under the supervision of Dr. Pietro Giuseppe Gucciardi. Today, I will present you my last research activity, which is the subject of my recently published paper in Sensor Journal entitled Fabrication of a Novel Electrochemical Sensor Based on Carbon Cloud Matrix Functionalized with Molybdenum Oxide and Two-Dimensional Molybdenum Disulfide Layers for Riboflavin Determination. Having now an introduction about riboflavin, which is a water-soluble vitamin of B group, and it is an important constituent of flavoproteins and play a vital role in the enzyme reactions in the human body as well as for animals that need a riboflavin supply to maintain stable balance in their bodies. Riboflavin is found in most food, with the highest content in dairy products, meat, dark green vegetables, mushroom, and fish. Supplemental riboflavin intake appears to have very protective effect on various medical conditions, such as anemia, and at the same time it also helps to reduce the risk of certain forms of cancer in humans, as well as protecting all the nervous system and promote a normal brain functioning. It also boosts the energy, increase the blood circulation, and protect the vision. That's due to the importance of this vitamin. Its determination become the focus of the researcher, and a large number of data are found in the literature about its electrochemical determination. Here we propose the novel nanostructured electrochemical sensor based on molybdenum oxide coated on the flexible conductive carbon cloth and decorated with molybdenum disulfide nanosheets. Previously, we have been investigated electrochemical sensor based on molybdenum material. This is the list of our publication in FlatChem, Sensor and Actuators B, and sensors. Let's have now a small introduction about molybdenum oxide, which is an N-type wide band gap around 3.2 electron volts conductor, which presents three crystalline structures, among which the orthorhombic phase is the most thermodynamically stable. Concerning the molybdenum disulfide, is a compound of the type MX2 with M's transition metal atom and X's chalcogen atom. It has an indirect band gap of 1.29 electron volt that turns to a semiconductor with a direct band gap of 1.9 electron volt going from bulk to monolayer, offering an important charge carrier mobility. Considering the promising properties offered by the two-dimensional molybdenum disulfide and the molybdenum oxide, the combination of these two materials appear to be very interesting in the fabrication of an electrochemical sensor. Hybrid molybdenum oxide molybdenum disulfide composites reveal more satisfying electrochemical properties than the pure molybdenum oxide and molybdenum disulfide. But the main limitation of pure molybdenum-based materials is their low conductivity. In order to increase this conductivity, molybdenum carbon composites have been largely investigated. And recently we used carbon cloth as a conductive substrate, which provide the required conductivity and a large surface area due to its network structure. Moving now to the aim of our work, which is first the preparation of the two-dimensional molybdenum disulfide molybdenum oxide carbon cloth composites, the development of the novel nanostructured electrochemical sensor based on molybdenum oxide coated on the flexible conductive carbon cloth and decorated with molybdenum disulfide nanosheets, and finally the determination of riboflavin. Moving now to the material synthesis, and the molybdenum oxide carbon cloth was prepared using a radiofrequency magnetron reactive sputtering, in which a percent of carbon cloth substrate were coated with molybdenum oxide layer and placed in a radiofrequency magnetron reactive sputtering with a customized down setup sputtering mode, in which argon is used as working gas, and oxygen as reactive gas in 1:5 ratio. The molybdenum metal target was fixed in the working pressure of 10-2 millibar for depositing a thin layer, A molybdenum oxide thin film was deposited on the carbon cloth substrates at deposition rate of 3 angstrom per second at 450 degrees. The surface contamination of the target material was removed by pre-sputtering the target at 0.01 millibar pressure for 10 minutes. The radio frequency power was set to 150 watts and the distance between target and substrate was maintained at 50 millimeters. Concerning the synthesis of molybdenum disulfide, a liquid phase exfoliation method was used, and the molybdenum disulfide commercial powders were acquired from Aldrich. The powders generally consist of flakes with lateral size of 6 micrometer. We started with ultrasonication for 30 minutes of molybdenum disulfide powder in sodium chlorate water solution. Then the dispersions are then transferred to hot and allowed to decant over the night. Finally, the day after, the supernatant is centrifuged on 1,500 rounds per minute for 90 minutes, and the solution obtained is collected for further use and also is stable for months. Moving now to the sensor fabrication, and here a small piece of the carbon cloth doped with molybdenum oxide was kept and deposited and fixed on the surface of the working electrode of the screen printed carbon electrode using the napkin, and then the molybdenum disulfide nanosheets was deposited via drop casting and left to in room temperature to dry. Moving now to the characterization, and first we start with some analysis, and here a picture of the modified two-dimensional molybdenum disulfide molybdenum oxide carbon cloth screen printed carbon electrode is shown in figure A. The network morphology of the two-dimensional molybdenum disulfide molybdenum oxide carbon cloth fixed on the working electrode of the screen printed carbon electrode is presented in figure B. Figure C presents perfectly the two-dimensional molybdenum disulfide molybdenum oxide carbon cloth composite, and molybdenum disulfide nanosheets are clearly seen on the top of the underlying molybdenum oxide nanoparticles. Its elemental mapping analysis, figure D, E, and F, of the two-dimensional molybdenum disulfide molybdenum oxide carbon cloth composite based on screen-printed carbon electrodes confirms the presence and the well distribution of the main oxygen, molybdenum, and sulfur atom on the surface electrode. Moving now to the Raman analysis, and here Raman spectra at 638 nanometer have been acquired first on the bare carbon cloth electrode, which is in black line, then on the carbon cloth dotted with molybdenum oxide, which is in blue line, and finally the two-dimensional molybdenum disulfide molybdenum oxide carbon cloth screen printed carbon electrode in red line. And on the bare carbon cloth, only the Raman fingerprint of carbon is detected, namely the DNG bent peak corresponding to the amorphous carbon phase present in the carbon cloth. On the molybdenum oxide carbon cloth signal, we observe the superposition of the carbon bands and the molybdenum oxide vibrational modes, which are attributed to the orthorhombic phase. And the final spectra of the two-dimensional molybdenum disulfide molybdenum oxide carbon cloth screen printed carbon electrode, the molybdenum disulfide signal is dominated. Moving now to the electrochemical tests, and the preliminary test was done to compare the electrochemical properties of different electrodes. Figure shows the current response of the different electrodes in the determination of riboflavin. The sensor employing the modified two-dimensional molybdenum disulfide molybdenum oxide carbon cloth electrode has the highest sensitivity towards riboflavin, improving the performance of all the other electrodes. And here the better sensitivity of the composite electrode can be associated to the increase of the effective surface area of the working electrode and the formation of the new electroactive sites formed at the interface between the molybdenum oxide and two-dimensional molybdenum disulfide. Based on these results, we have evaluated the response of the two-dimensional molybdenum disulfide molybdenum oxide carbon cloth-based sensor at different riboflavin concentrations going from 0 to 40 micromole using the linear sweep voltammetry as presented in figure A, evidencing the associated augmentation of the peak current value. In figure B is shown the calibration curve of riboflavin, plotting the peak current as function of the analyte concentration, and the sensitivity, namely the slope of the calibration curve, is about 0.67 micron per micromole minus 1, and the low detection limit was 1.5 micromole. Tests were repeated after almost 1 year using a new prepared two-dimensional molybdenum disulfide nanosheet suspension for replicating the fabrication of a new two-dimensional molybdenum disulfide molybdenum oxide carbon cloth screen printed carbon electrode sensor in the same condition of the first one. And as presented in the figure, the two set of data points can be fitted almost well from the same linear relationship. The reported findings suggest that the electrochemical properties of the two-dimensional molybdenum disulfide molybdenum oxide network structure, as well as the fabrication procedure of this platform, can be replicated very well, leading to sensor devices with reproducible response. Concluding our presentation, two-dimensional molybdenum disulfide molybdenum oxide carbon cloth nanocomposite electrodes were prepared and tested for the electrochemical detection of riboflavin. The structure was used for fabricating a novel electrochemical platform with enhanced properties with respect to the conventional commercial devices and those prepared with a single constitute. This unique two-dimensional molybdenum disulfide molybdenum oxide carbon cloth screen printed carbon electrode platform resulted in promising sensor device for the electroanalytical determination of riboflavin. As a perspective, we will test the two-dimensional molybdenum disulfide molybdenum oxide carbon cloth nanocomposite electrodes for the electrochemical detection of riboflavin in real sample, and to fabricate flexible and self-standing two-dimensional molybdenum disulfide molybdenum oxide carbon cloth nanocomposite electrodes. And thank you for your attention.
Thank you very much for your presentation. I see that there is a question. Please, Malara, make a question.
No, sorry,
You pushed the
yes.
wrong button.
Yes,
Okay.
sorry.
Okay, no problem at all. I have a simple curiosity. Why did you decide to use carbon cloth for substrates?
In fact, it was the first was the carbon cloth doped with molybdenum oxide, and this was a sample from our collaborators, which already we have a published paper with only this sample. And after since I'm working with the two-dimensional molybdenum disulfide. So we wanted to make this this kind of composition molybdenum oxide, molybdenum disulfide, and we wanted to test before because we tested before the molybdenum disulfide alone for riboflavin, and we didn't have a very good response. So adding the composite of the carbon cloth doped with molybdenum oxide, we saw like enhancement, a big enhancement in the response.
Yeah, it works pretty well.
And also the molybdenum disulfide is a semiconductor, is not really a conductor. So with the presence of the molybdenum oxide and on the carbon cloth, we can increase the conductivity, so we can increase the electron transfer and can enhance the response of the electrode.
Okay, thank you. Thank you very much.
Well,
so we can proceed to the last talk of this early afternoon section. So we have the talk from Chaturanga Kumarge from University of Brescia, and the title is Thermal Oxidized Cobaltum Oxide Nanostructures for Gas Sensing. Please proceed.
Good afternoon, everyone. I'm Chaturanga. Today, I'm here to talk on the growth of cobalt oxide nanostructures for the ethanol gas sensing. As it is known, the use of ethanol-based hand sanitizers disinfectant has been exceptionally increased around the world due to the health emergency. In this case, it is important to consider the impact of their usage on the health of the people all the environment, since ethanol is highly affected to the skin irradiation, lethargy, eye and breathing difficulties. Furthermore, the recent studies have shown existence of ethanol in the urine of non-alcoholic people upon the exposure. In this scenario, monitoring and quantifying the ethanol in the environment is highly important. Chemical gas sensors are one of the best tools to detect the ethanol in means of highly sensitive, stable, and low cost of production. In general, there are two types of metal oxide, or N-type metal oxide and P-type metal oxide. The N-type metal oxide are highly investigated compared to the P-type metal oxide. However, the rapid growth on the P-type metal oxide exists annually. In this scenario, the study was focused on preparation of cobalt oxide nanostructures and its morphological and structural characterization and fabrication of conductometry devices and gas testing. So let's focus on the overall study. The overall study is started with cleaning of the alumina substrate, and later this alumina substrate was used in the sputtering for the deposition of the cobalt and the metallic cobalt with a layer of 50 nanometers and 100 nanometers, and ultra thin platinum layer was magnetically sputtered on top of the cobalt layer. Later, the thermal oxidation of the sputtered metal layers were employed at 800 Celsius for 4 hours at temperature of 0.14 millibar and with the presence of oxygen and argon flow. And later, the fabricated materials were examined in XRT and for the field emission assay. Then the devices were fabricated and the possible gas testings were carried out in this study. Let's focus on the results. The figure shows the XRT pattern of the obtained nanostructures of cobalt. So figure confirms the fabricated cobalt nanostructures are in the phase of a cubic phase with the CO3O4 form. And it also shows the reflection peaks from the platinum catalyst, and all the remaining other peaks belongs to the alumina substrate. Let's focus on the morphological characterizations. The figure left shows the field emission cm micrograms of obtained nanostructures, and it confirms the formation of nanowire structure in the cobalt oxide with the applied conditions. And figure right shows the highly magnified field emission SCM microgram at the regions of the alumina substrate and the cobalt layer. It shows different stacking layers, and which can be further analyzed as shown in the figure middle. Then the device fabrications were exceeded, and device fabrications were started with depositing of the platinum interdigital electrodes as well as the platinum heaters. Then this device were mounted on the TO package by using the electrosoldering the gold wires. Later, the fabricated sensors were mounted on the gas chamber for the possible gas testing. Let's focus on the conductometry measurements. The conductor measurements were started by analyzing the conductance of the fabricated sensors at different working temperatures, and it shows the semiconducting nature of the fabricated sensors. And the figure middle shows the dynamic response of the sensors to the ethanol at different working temperatures and exposure to the humidity conditions. And it shows the P-type semiconducting behavior of the fabricated sensors, and when furthermore it shows the hindering of the sensor's performance when exposed to the humidity conditions. And figure right shows the sensor's response upon the working temperature of the two different sensors, and we can conclude The best working temperature for both the sensors having thickness of 50 nanometers and 100 nanometers are exist at the working temperature of 300 Celsius. Next, next, the samples were analyzed for is response time and recovery time. The figure left shows the dynamic response of the fabricated sensors at the working temperature of 300 Celsius, both in dry and 40% humidity conditions. And figure middle shows the recovery time and the response time of the fabricated sensors. In general, the response time and the recovery time was found to increase with the ethanol concentration. And also, it can be concluded this response and the recovery times are overestimated, as it is known, a 15 minutes of approximation is necessary to complete atmospheric change inside the gas chamber. However, these values can be used to qualitatively identify the sensor's performance. So it is important to discuss the gas sensing mechanisms also. The gas sensing mechanism of the sensor can be discussed under three major sections called absorption of oxygen, catalytic effects, and the structural effects. Let me discuss the absorption of and the oxygen vacancy effects on the gas sensing mechanism. So in here, the gas sensing mechanism is based on the gas absorption and desorption mechanism. First, oxygen molecules are absorbed onto the surface, and these oxygen molecules forms the oxygen species. These oxygen species are the active sites for the ethanol detections, and which can be further understood by the equations of A and B. Furthermore, the absorbed oxygens fills the anion vacancies inside the metal oxide. And these anion vacancies improves the ethanol dissociation and is improve the gas sensing mechanisms as shown in the equations C and D. Also, in the catalytic effects, the major catalytic are the CO3 cations, CO3 plus cations. When ethanol is absorbed, the CO3 cations react with the absorbed ethanol and which reduces to CO2 plus. So when this catalytic effect occurs, the ethanol is oxidized into carbon dioxide and to the water. So in addition, structural effects are also interested when concerning the gas sensing mechanisms. So as shown in the figure right, several defects can be exist inside the prepared sample. So in here, we can see several pores, and these pores are especially interesting when the pore size is comparable with the mean free path of the ethanol. When pore size is equal to the mean free path, the condensate diffusions will prominent, and where the collisions between the wall and the ethanol molecules are highly dominant, and which improve the sensing mechanism of the sensor. So this table summarizes some recent studies on detecting of the ethanol by using cobalt oxide one-dimensional nanostructures. So in here, we would like to say this study has shown the possibility of detecting the ethanol at these lower concentrations compared to the recent studies. Furthermore, the fabricated sensors were further analyzed for the detection of the hydrogen and carbon monoxide. And in conclusion, the sensor has shown significant response towards the hydrogen and carbon monoxide compared to the ethanol. So, in conclusion, we can say the cobalt oxide nanowires can be successfully grown by using simple locus thermal oxidation methods, and fabricated sensors have demonstrated the possible applications of cobalt oxide nanowires for the ethanol detections. However, the humidity has hindered the sensing mechanism. Furthermore, Fabricated sensors will be investigated for the further studies in the means of its stability, repeatability, and for the sensing performance towards the different gases such as NO2, ammonia, and acetone. And furthermore, some material characterizations such as high resolution TM, XPS, and Raman studies are still further going on. Finally, we would like to thank the MURI and the NATO organizations for their final assistance. Thank you very much.
Thank you so much. Now, are there any questions about this talk? It seems, are there questions? Seems not. I have one. You showed us a lot of mechanisms regarding the gas sensing response. Did you prove these mechanisms or these are from literature?
It's a very good question, Professor. Actually, the first two, that means the oxygen absorptions and the catalytic effects, we can understand. But the third one, that is with the condensate diffusions, is from the theory literature.
Okay, okay. Thank you so much.
Thank you very much, Professor.
We can close this afternoon section.
We now have the Assing Award for the best oral presentation on sensing technology. Let me say, of course, we need more time. I mean, we did our evaluation in progress according to presentation, but for sure, we need 10 more minutes to make a very more accurate evaluation of the oral presentation. So may I ask you to connect again in 10 minutes time? Let's say now it's 5:15. May I ask you to be connected within 10 minutes time and to have this proclamation of the Assing Award. Thank you. So we will be connected again within 10 minutes time. Please stay connected. Thank you. Here we are again. I thank you for your precious time, and the scientific committee has carried out throughout the day an appraisal and evaluation of the oral presentation, and I'm glad to announce you that the Assing Prize for the best oral presentation has been awarded to Dottoressa Barbara Fabbri from the University of Ferrara for her presentation regarding thin titanium niobium oxide solid solution for gas sensing application. We are very glad it has been a good, convincing presentation, and so we thank Barbara for all efforts she did. So at this point we can close this today's section dedicated on materials for sensors. As I told you, this presentation, the whole day will be on YouTube. I'm not so friendly with the social. That's the first time I am in video. I don't know how will be. By the way, I thank you all, and please be connected tomorrow with materials for energy. That's quite interesting matter regarding photocatalysis and so on. Thank you again, and have a good evening.
Congratulations to Barbara.
Yeah, congratulations. Thank you.
Thank you. Thank you so much.
Okay.
Thank you.
Bye-bye.
Bye-bye. Bye.